announcement. Tonight we have the dinner on the program at 7:30. We shifted a bit ahead, so it's going to start at 7. It will be a very nice raclette in the room where we had the breakfast. And we will end at 6, so we'll have 1 hour essentially of free time to rest a little bit before dinner. And then we meet at 7 there. We will re-announce that before the dinner. And this morning we have the pleasure to welcome our new speaker, Thiran from EPFL. He's local almost, and he's making the pleasure to come here and give presentation this morning and this afternoon.
Thank you very much, Pascal. So thank you for the organizers for inviting me to this winter school. So when I was thinking what topics to present that you might not know and might use and might be useful in the context of a winter school, so I started from some of the paradigms that you all use in terms of networks. So it's certainly going to be about networks, and typically what we have more and more is, of course, the scale explosion, the fact that the components are often very simple, low cost, and essentially that they evade fine-grained control. So essentially it relies a lot on self-organizations, and they have to work sometimes, not always, but sometimes under adversarial conditions. They need to cope with failures. They might have a very dynamic, time-varying environment. And so the two parts that I will cover, the first part this morning has to do with a probabilistic analysis. So everything is geared always towards performance analysis. That's a little bit the area I am in. Laurent yesterday was mentioning among the different metrics one of them, and that's definitely the case. And I would say the first one is geared about the targets a probabilistic analysis of large networks. And essentially there what we're interested in is usually in deriving some macroscopic properties for performance analysis. For example, how throughput scales, how delay scales. And so these kind of quantities we need to derive macroscopic properties, but from a network made of a large number of small components. And the methods that we have been using quite successfully are very often inspired from statistical physics, because of course physicists, they are used to deal with large ensembles of atoms that are even much simpler than any nodes we might have in our networks, and derive macroscopic properties, magnetization, and so on, from these components. And one theory that we have found very useful is percolation theory. And so the goal here, I was thinking, it took us quite some time to enter in this field. It's actually a very, very interesting field. So the goal of this morning will be first to give you an introduction, I would say a crash course on percolation, by taking really like the most useful pieces of that beautiful theory that we found useful and then to show you how we have used that in order to derive tight bounds in connectivity and in throughput scaling. So essentially it's a paradigm that changes a little bit the view we have in networking, which is classically the view we have that. Another models which I finally decided not to go over, so because to have enough time, and since we don't want to take too much time, is a model from statistical physics known as a hardcore model. But I will focus only on percolation theory, so this morning to make everything fit in 3 hours. And so these are typically things that you would apply if you have sensor networks with a very large number of nodes, and so mostly wireless networks. And then this afternoon, I switched completely gear, and I'll give a crash course on something I've worked on long ago, which is therefore targeting no longer probabilistic, but a deterministic performance analysis. So in this case, we are working to obtain in networks worst case guarantees. And the goal is not so much that we have a lot of, so of course we can have large networks, but essentially their behavior is a little bit too complex to be described by traditional queuing models successfully. And that's the realm of network calculus. So this is more, the goal here is more to obtain provable guarantees, a little bit what Laurent mentioned yesterday, when you want to have certifications that you will never have under any circumstances a delay that exceeds or loss that exceed some amount. How do you do that? And so that's, I will give an introduction to network calculus. Again, it's a very different setting. So this is based on so-called tropical algebra, so max plus min plus algebra. And we call it calculus. You'll see in 1 hour why we call it calculus with Jean-Yves. It's because it's a bit a gymnastic that you do with the brain in the sense that addition is replaced by minimum and multiplication is replaced by addition. So you do everything like a classical system theory, but it takes a little time to get used to this change of the things. And so this was developed more first for diff-surf and int-surf, so reservation-based services and priority services in the internet, at a time where essentially design was done mostly by over-provisioning. So everything was best effort. And now it takes over again, I would say, because, well, you have first embedded networks. For example, the one that is used, the full duplex network used in the Airbus A380 uses some of network calculus to have, these networks, of course, you need to have really certified, guaranteed, on networks on chip and on these settings as well. And so that we do this afternoon. Okay, so the program is like this. So I don't think I'll have time to speak about source location. I'll speak mostly about percolation theory this morning. So I'll first introduce why actually it's an interesting field and why we were looking at it as a modeling tool for performance analysis. And then I'll give a little bit of crash course in 1.5 hours about what's called bond percolation. So that's the simplest form of percolation, but essentially, once you understand that, you understand qualitatively percolation in many other models, and this is the study of phase transition. It's actually one of the simplest models in statistical physics that exhibits very interesting behavior as phase transitions, and though there are 3 phases, before, after, and during the phase transition, and then we'll go back how we have applied this kind of techniques, what they have told us about wireless networks. And then in the afternoon, then I'll introduce the 2 basic concepts, which are ROI curve, how you describe traffic, and service curve, how you describe the element in network calculus. And then we'll go over 3 fundamental bonds and actually how you can derive things very easily using that stuff. And finally, a case study to show a little bit how you put in equations, I would say in max plus and min plus equation, a particular system, which would be for video streaming and video smoothing. Okay, so we start now with a percolation and wireless network. So let me start first by giving the main references that we have worked with and that I recommend. So for the part on bond percolation, so that I'll follow very closely this textbook by Geoffrey Grimet, who was the reference certainly for 2 or 3 decades, and which I really recommend. It's really extremely well written as a textbook. It has everything you want in it, and so if you need one day percolation, I really recommend it. There are more recent references as well with new results that are, of course, from very famous people as well. For the part on application to wireless network, there's a couple of textbooks called Stochastic Geometry and Wireless Network by François Baccelli and Bartek Bacechin. For me, they are a little bit, for those of you who have done performance analysis, there were two classical books by Leonard Kleinrock, was Theory of Queuing Systems and Application of Queuing Systems. And queuing system essentially at the time was, just looking at a time arrival of packets, calls, whatever, into a system that were processed, and then after they have received a service, were sent further away. They have reshaped that a little bit, similarly with a volume theory, a volume of application, where essentially they redo a little bit the queuing theory, but for spatially embedded networks, such as wireless networks and so on. So that's a viewpoint which is very interesting. And that's more the applications, I would say, to continuous stochastic geometry. So this is discrete. It's easier mathematically than the continuous one. You'll see in a moment why. And so these would be references I would recommend. So let us start with percolation. So percolation essentially has the name, from having a porous material, and then you have some density of holes in the material, and you pour water in the material. Now, the density might be not too large, in which case, your water here fills in only superficially and doesn't go deep into the material. That's what you would like to have, if you do walls and you construct this. If, on the other hand, you have something like your morning coffee, you like the water to drill and to go all over. And so the study of percolation is essentially that there is some density of holes from which you go from having only a finite depth of incursion here of your liquid to something that goes infinitely deep into the material if you had an infinite piece of network. This is called the subcritical phase. This is called the supercritical phase, and this is the critical threshold. It turns out that in materials, it's not something that is proportional, so the depth at which the water here fills in is not proportional to the porosity. There's really a sharp threshold about which suddenly this water drills in. Now, for us, the model that is the most famous one is the so-called Boolean models. And that's a model that was proposed in 1961 already, with already an application motivated by, at the time, it was called packet radio networks. So we just reinvent things later with ad hoc network, sensor network, but we don't know what comes next. But essentially there, you throw nodes in a plane, and so you throw them according to a Poisson process, or equivalently, if you have a finite surface, you draw a uniform number of nodes on this surface. So you have lambda nodes per square meter or per unit of surface. And you simply declare that two nodes are connected by an edge if and only if their positions in the planes are not separated for more than some radius r. So there are two parameters in the model, lambda, the number of nodes I have per space unit, and r, which is the radius between which you connect these two. And so, of course, the larger r, the better the connectivity. And this was used, I would say, as a first model of an ad hoc network, sensor networks. And there are two main approaches to look at this. The first one is to deploy all the nodes on an area of size AN, and logically, especially if you are networking, what you want is to connect everyone. So you wonder how large should be the radius R so that the entire network is connected. It's called the full connectivity approach. The second one doesn't start with a finite area that you grow with N. You start by throwing all your nodes on an infinite plane, and that's the percolation approach. So if I go a little bit between the two, the first approach, you take a finite area, you throw some nodes, and you grow this area, but each time during the process, the area is finite. Okay? And so you just increase it progressively. So here I keep a constant density of nodes, you increase that, and you want that as n tends to infinity, well, the graph is fully connected. And so you have a sequence of graph, each of them is finite, and you look if that sequence will become connectivity. So the good connectivity here means full connectivity at each of these different snapshots. And in the book dealing with, by Matthew Penrose, this is what he calls the connectivity regime of random geometric graph. And the radius needs to grow with n, and needs to grow as the square root of log n over n, so that as n tends to infinity, the graph of n nodes with this radius will have every node connected, so not in a single hop, of course, but will be connected, so all the nodes will be connected to each other. There is a path from every node to the other one. And so that is the so-called connectivity regime. The second approach, percolation, you start immediately with an infinite plane, so you cannot ask, since you have an infinite number of nodes, the same question exactly. So what you ask is, how large should the radius be, so that you have a giant cluster of nodes, so that essentially all nodes except little o of n would be connected to each other. And so this is, so if we take a restriction of this to an area of an with n, which is roughly the density of the Poisson process times the surface, then we would fall back into one of the snapshots of the previous model. But for having a giant component, you don't need square root of log n over n. You need something much less, which is 1 over square root of n. So you have typically two transitions, one which is the so-called connectivity transition, and the other one, which Penrose called the thermodynamic regime, which is in 1 over square root of n. And so this occurs, the giant component occurs much earlier than the full connectivity. And there are benefits for that we are going to exploit. So we are going to look at percolation, so the emergence of a giant component, and not so much having all the nodes fully connected. You'll see how we deal with that in networking applications later on, okay? So lots of work, that's for the fully connected domain, and for the infinite domain percolation theory, essentially to find the value of R and lambda. If I look at pi R square lambda, that's the average number of nodes connected to a particular node, so this is the average node degree, and to find the value at which, the threshold at which it occurs. It's still an open question to know that exactly. Essentially, there are bonds that are closer and closer as time went on. It's close to 4.51, but we know it only numerically for this model. That's why it's already a difficult model to work with. Okay, so the main property of continuous percolation is if I take this Boolean model, and if I take it on the plane or even on a higher dimension, then I have this kind of behavior. So theta, which is a probability that depends both on the connectivity radius and the node density, will be the probability that an arbitrary node, which will place at the origin without loss of generality, belongs to an infinite cluster. Well, then the behavior is like this. Essentially, there is a threshold, which is expressed here in terms of lambda r square. So in pi multiplied by pi, that would be the critical node degree, below which this probability is equal to 0, strictly, and is strictly positive and growing very fast if I am above this threshold. And for me, the fascinating aspect of percolation is, if I look at it from an engineer, something which the first time I saw that, I found that really intriguing, is if you take a network with a radius, so here I will keep lambda the same, and I will just increase r from a value here to a value here. So here I am slightly subcritical. So I have some radius connectivity, radius r, which is just here. And all the colors here that you have on the pictures represent different clusters of connected nodes. So if you take two nodes, for example, one here on the green one and one here on the purple one, well, they belong to different clusters of nodes that are connected to each other, and clearly there's no path between each other. And now, as an engineer, you could say, okay, you need to connect most of the nodes, in particular these two guys, but most of the nodes, by adding the minimal number of edges in this graph. How you would do, you would say, okay, well, that's, when you see that, it's clear that you would probably, try to put an edge, here, and you need to put them, so that you connect most of the clusters. So you can see that if I add a few edges, I probably can connect most of these islands together. But I would have an algorithm, or I need to do a choice that is very smart to do that, right? I need to look at this. For me, the magic aspect of percolation is that if I say, okay, I will increase the range of connectivity by a small amount, just here, it does exactly the job. Okay, so instead of having to choose where are these edges, spontaneously, all the edges that I needed to have, or most of them, are there. In particular, if I want to connect these two guys, now I have a path. The two are not very different. There are only a few black edges that are added. But I would say I would not have made, by an algorithm, a much better choice than what naturally increasing the range has done. And that's the phase transition. I even have more than one path connecting the green vertex here and the purple vertex here. And here, of course, I still have some isolated nodes, right? Or even a cluster of two. So I have few, not every node is connected, but the vast majority is connected to each other. And so I go from one to the other quite suddenly. And the first time I saw that, if you're used to it, it's probably you get used to it. But the first time I saw that, I found that quite surprising to do. Now, the difficulty with studying already this model, it's not a very realistic model of wireless network, right? In particular, we are going to see that we neglect interferences here, and that we'll need to take them into account. But it's already a very difficult model to study because we don't know analytically already this part here, so we can prove that there is a phase transition, that this behavior exists, but there are few analytical tools that we can use so far to study this. And so a much easier model that keeps the same qualitative behavior as the previous one is a discrete band percolation model, and that's where I'm going to spend most of my time before coming back to the continuum model. So for this one, we'll do a bit more theory. So we need to set a few notations. What is band percolation? So it's simpler because I have one parameter. So basically, I take a lattice, the square lattice here in 2 dimensions. Okay, so I have a grid, and I have these different edges, which I keep with probability p, and I delete with probability 1 minus p independently from each other. Okay, so what I have here, each edge is open, so it's kept with probability p, and deleted with probability 1 minus p independently from all the others. So extremely simple. So what I have there is that essentially events that I will have, which will be defined in terms of open and closed edges, they depend on a single parameter p, which is the open edge probability. That's the only parameter that I have. And I usually will put that as an index of this measure because sometimes I will change p, and so it's good to remember what it is. Then I need to look at open path. That's a path which is made only on open edges, closed path of closed edges, and some notations. Two vertices here, x and y, are connected to each other if there is an open path that connects x to y. What I'm particularly interested in is if I pick a vertex, in particular the origin, so if I pick X, I look at the size of all, the cluster and then the size of all the vertices that are connected by an open path to X. And C will be the one, so one of the vertex will be the origin. All the vertices that are connected by an open path to the origin will be called C. And finally, sometimes I need to have some finite pieces of my lattice. So I call a box, essentially, a 3. Well, that's the Cartesian product of minus 3, 3 times 3, 3. So that would be the box B3. If I center it somewhere else than 0, then I move it to some vertex X, just here. So this would be a realization, typically, of a bond percolation setting. You see, I have kept the open edge here, the closed edge are just here. And so I am interested, for example, is 0 here belonging to a cluster which is finite or that spreads infinitely in the network. Okay, so that's what I have. So essentially what I'm interested in is the percolation probability. In other words, does the cluster of the origin, all the vertices that are connected to the origin by an open path, is that, since I have an infinite lattice, is the number of vertices infinite or not? That's the event when the open edge probability is P, and I call that theta of P the percolation probability. The threshold will be the largest P such that theta of P is equal to 0. Above that, it becomes strictly positive. And one of the main questions that we're going to see here, in short, I'm going to skip the difficult proof. I make my job easy. It took, I think, 20, 25 years to find the answer for that, is what is the critical threshold here for 2 dimensions? So what are the main questions? Well, the first one is first to prove that there is a phase transition. Is there indeed a value PC? We know that if P is equal to 0, all the vertices are isolated. If P is equal to 1, the network is fully connected. But is there a value PC from which you go from a percolation probability which is 0 to a percolation probability which is strictly positive? That's the first thing to do. That's relatively easy to do. And then, if so, then there is a phase before PC, in which the probability of percolating is equal to 0, but what is the mean cluster size? What are the tail of the distribution? What is the diameter? How are those clusters? That was the left pictures I had here. So what are the size of the different clusters that I have? In the supercritical phase, well, I know there is the origin belongs to an infinite cluster, but do I have one or many infinite clusters? And then those nodes that are not in the infinite cluster, what is typically the distribution of the clusters that I have just here? And finally, the main question is, what is the threshold PC, right? Can I compute it exactly? And what interests mostly physicists, it's a little bit different from engineers, you're going to see. We like to work in supercritical phase at least, right? We want most of the nodes to be connected. The intriguing phenomenon is what happens exactly at the threshold. That's where mathematicians and physicists spend more of their time, because that's the most difficult thing. So, is the percolation probability continuous or non-continuous at 0? You have a phase transition. Is the mean cluster size finite or infinite? What is the distribution of the clusters for large N just at the critical threshold? So that's what we are in. We're first going to show that indeed there is a non-trivial phase transition. And essentially, it's easy to show, and we're going to do it now, that the critical threshold is between 1/3 and 2/3. How we do that? It's a simple counting arguments for the first part. For the first part, what you do is to say, okay, if the origin, here belongs to an infinite cluster, well, it means I can find a path of an open path of length 1, of length 2, of length 3, of length 4, and of all length, right? Because if I find an open path up to length 17, but not above, it means that, the number of vertices is certainly finite. So I count simply the number of walks I can do from one vertex, which I take the origin here. So how many different paths can I find? self-avoiding so that do not take twice the same edge. Well, I have 4 possibilities for the first one. And then when I am here, I have 1, 2, 3 possibilities. And I have never more than 3 possibilities, because the edge I come from, I cannot retake it over. Of course, I have much fewer than this, so the number of self-avoiding more is definitely much less than this, because sometimes I would meet a guy, you know, that I have already encountered, so I have only 2 possibilities, but I know it's never more than this. Okay? So it's really loose, but it's going to make the job here. And then I count the number of open self-avoiding path of length n starting from 0. I call that n of n. So the percolation probability for sure must be less than the probability that for any integer n, I find at least one path of length n. Okay, if I don't find an open path of length 19, then it means that I have path up to length 18, but then I cannot go to infinity, right? I must stop in 18 edge. So I must have that. And this probability is certainly less than, much less than the expected value of n of n, right? This is the sum of all the little k probability that n of n is equal to k. It's certainly more than this thing here. And what is the average number of open self-avoiding path of length n? Well, it's equal to sigma of n, the number of self-avoiding path, times the probability that all edges on that path are open, which is p times c times n times, since I have a path of length n. So the percolation probability for n is always less or equal than this. Now, sigma of n is less than 4 times 3 times n minus 1. So this is certainly less than 4 times divided by 3, and then I put the 3p under n inside here. And so if p is strictly less than 1/3, you see that this quantity here tends to 0 as n tends to infinity. In other words, the percolation probability will be 0 if p is less than 1/3. So the threshold must be larger or equal than 1/3. If I'm below 1/3, I'm for sure going to have a percolation probability which is equal to 0. So that's just based on this simple counting argument. Okay, so that's what we do. We know it's above 1/3. Now, in the other way, it's an argument in physics which is using the dual of the graph. It's called Peirce's argument. It's a very powerful argument. So what I do is I don't count directly the open path. I take the dual lattice. How do I construct the dual lattice? I will place a vertex inside each of the little square here, and I will connect 2 vertices here by an edge. And if that edge crosses an open edge of the primal lattice, it will be open. If that edge crosses a closed edge of my primary lattice, it will be closed. Okay, that's how I construct the dual lattice. So in the little circles here, I have my dual lattice here, and you see I keep an open edge whenever it crosses an open edge of the original lattice, and I keep a closed edge whenever it crosses a closed edge of my dual lattice here. So that's what I have. And now, before I do that, so if the origin here does not belong to an infinite cluster, well, it means that I cannot go whatever path I do, I will be stopped at some point. So I will have edges that are closed at some vertices here. And so if they are closed on the dual lattice, all the edges will be closed as well. And so if I do that, what I will have is I will have a circuit that is completely closed. If I find the circuits like the red one here, then it means essentially the cluster of vertices connected to the origin is completely contained, is encircled, and must be finite. If I don't find any of these circuits, it means essentially I cannot encircle the cluster at the origin, and therefore I have an infinite cluster in my network. So what I'm going to do is count how many circuits like that exist. Yes. The dual lattice, how I construct the dual lattice.
Yeah, but like why?
Oh, why? It's just that it's to express this closed circuit, it's easier to express in the dual lattice than in the original lattice. It's just to view it as essentially I need to have a closed circuit, but the closed circuit is defined in the dual lattice rather than the original lattice. But it's just a it doesn't contain any new information from the original lattice, right? It's completely defined from the original lattice. It's just that if I have to draw this circuit, it's easier to define it properly on the dual lattice. Just for that reason. Okay, so what I'll do is actually I'll take two events. The first one is this red thing. So essentially, I'm going to take a box of size M. Just, you'll see in a moment why I need to take. So not just the origin, but a square of size M just here. And I ask two things. I say that within the square, all the edges, so within the box, all the edges are open. Since it's a finite box, it's a positive probability that all edges are open. It's P times the number of edges that I have in the box. And then I ask that there is a closed or circuit, or rather that there is no closed circuits if I want to have an infinite cluster, that encircles that box Bm. Okay, so I ask that Fm does not occur. So the percolation probability, this time I look for a lower bound. For sure, if all the edges in the box are open, so I can go everywhere in the box, and I don't find any closed circuits in the dual lattice encircling that box, then for sure my node placed at the origin here is connected to vertices that are infinitely far away from it. So the number of vertices connected to the origin is infinite. And so the percolation probability is certainly larger than the probability of the joint occurrence of these two events. Since G of M is defined within the box and Fm is defined outside the box, they are defined on independent sets of edges, and so the two are independent, so it's a product that I have just here. Now, this probability is strictly positive because M is finite. So remember, to be in the supercritical phase, I just asked that the percolation probability is strictly positive. So that's fine. So I need to work on the probability that I don't find a circuit surrounding a box of size Fm. So I need to compute the probability that it does not occur or the probability that it occurs, and I'll take the complement of that. So how do I do that? Well, again, it's a counting argument. I will count the number of closed circuits that are length at least 8m. 8m, why? Because that's the perimeter of my box, which has a side to m. So if I do that, I take a self-avoiding bulk. So if I take any circuits of length n that surrounds the origin, well, I cannot go too far away. So if I assign a circuit a tour of length n, the further I need to go on the left, I will need to go on the right of this vertex. I'll need to pass through an edge which is in the dual lattice on the left of the origin. I'll need to pass through an edge on the right of the origin. But if I take n over 2, an expression of n over 2 edges here, one edge here, I need n over 2 to come back, so I cannot go too far to the right? So what I need to have is that at least one of the edges at the right of the origin, but that are between edge 1, edge 2, edge 3, up to edge n over 2, must be taken by these closed circuits. Because if it doesn't take it, then it would need to take an edge which is further away. But if it takes an edge which is further away, essentially he cannot come back within n edges to the origin, right? He has a limited budget, which is n, so I know that I have that. So what I do is I will take for each of these possible edges, well, I do a self-avoiding walk of length n minus 1. I know an upper bound of that. And so that will be a very, again, loose upper bound on the number of circuits that I need to have. So the number of such circuits will be less than n over 2 edges, that will be one of these edges at the right, times the number of self-avoiding walks that I can do of size n minus 1, because I've already consumed one edge for doing so. And so the probability that I find a circuit around the box is certainly less than for all n starting at size 8m of the probability of finding a closed circuit of length n. And if I replace that by what I have just above, this is less than n over 2 times sigma n minus 1 times the probability that all edges in the circuits are closed. So this time, this is 1 minus p, because I want every edge in that path to be closed. And so if I put that, again, using the fact that sigma n minus 1 is less than 4 times 3 n minus 1, I have here something which is 3 times 1 minus p to the power n minus 1. And so you see that if I take m large enough, I can make this always less or equal than some quantity such as 1/2, provided that 3 times 1 minus p is strictly less than 1. That means 1 minus p must be larger than 2 over 3. And so in this case, the percolation probability is for sure larger than the probability that this does not happen, and a strictly positive probability of GM. This does not happen with probability at least equal to 1/2, 1 minus this probability. And so the percolation threshold, theta of p, is, the percolation probability is strictly positive for p larger than 2/3, so the percolation threshold is certainly less than 2/3. Okay, and so that's a technique of finding these closed circuits, which is used in statistical physics, which is called Pearl's argument, which is used like that. Yes?
You've used the square grid, and then some people like to use hexagons in the time.
Yeah, so there are many others. There are some for which it's easier to find it, and then others for which, proving it, I can use that systematically. Finding the exact value, you'll see some are difficult, some are easy. So, but that technique can be used exactly for all the text here. So the first one is to say, well, if p is small enough, I see that I cannot have infinitely long path, and I count the number of paths I have, I see that it must tend to 0. And the other way, I see that if I want to have something infinite, I cannot find a closed circuits, and I see that the number of closed circuits is actually vanishing if p is too high, because 1 minus p is going to be too small, and that's exactly the technique that you use. So this shows each time that there is a phase transition, and that's it's a powerful technique. The counting arguments is very loose, but it's sufficient for doing the job, right? It's really far from it. So here are simulations of what you would do. So we know that p is equal to 1 and 1/3 is subcritical. That's proven here. Actually, if I take 0.49, it's less obvious, but this is still subcritical. That's not proven here. We know that if p is 0.7, that would be a piece of the grid, this would be supercritical, and in particular, you see that it's easy to find an open path that goes from the left to the right, or that goes from the bottom to the top, right? There are plenty of open paths like this. This grid is less obvious to find this path, right? Again, if I take that to an algorithm or to a human, it's a little bit a maze. Do you find you have that, I don't know, in some magazines for kids, how to connect, is there an open path connecting this to this one? I know there is one because the density is, but it's not so obvious to find, but there are actually such paths, but it takes some time. So that's what we have here, and actually, you see, we know that the threshold is between 1/3 and 2/3, but you see on the simulation, even with a large finite grid, that you have something very sharp here, so it's 0 and it goes to 1. Now, sometimes there's a confusion between these two probabilities. One, the probability that we are looked at is a probability that an arbitrary node or vertex belongs to an infinite cluster, and we said the origin. The other one is the probability that there exists somewhere in the lattice an infinite cluster. I might be unlucky. I might have taken, you know, in this case, for example, if I pick this guy here, well, it belongs only to a finite cluster, right? It does not belong to the giant component. So it's normal that, especially here, not every node belongs to it. It tends to 1 very quickly, but it's exactly 1 only when p is equal to 1. So there is always an infinite cluster. That's a consequence of the Kolmogorov 0-1 laws, because essentially, if I have a sequence of independent random variable with finite moments, I have here what's called a tail event. So an event is a tail event if it does not depend on finitely many of these random variables. For example, if I look at the sequence of random variable and I check whether the sum converges or not, well, if you change, you know, 3 of them, it will not change the fact that it converges or not. So that's a tail event. If I take the average, same 2, if I take n tending to infinity. But on the other hand, if the sum converge, on the condition of that, well, the fact that the sum itself is less than 3 might depend on finitely many of these random variables. Because if I have 299, I change, you know, 3 small one by replacing by 3 large value, then I exceed this threshold. So a change of just a finite number of these random variables may bring this to a value strictly more than 3, so it's not a tail event. And Kolmogorov 0-1 law says that whenever I have a tail event, its probability is either 0 or 1. Now, having an infinite cluster does not depend on finitely many edges. If you have an infinite cluster, you close, you know, 10 edges, it will not change the fact that you have an infinite cluster. And vice versa, if you have a finite cluster, you open 10 edges, it will not become suddenly infinite. And so it's a tail event, so the probability that there exists an infinite cluster is always going from 0 to 1. Okay, so that's the difference between, so that's why really there is a phase transition. Suddenly, if I have a large number, I know that I have a giant component with probability 1 above the threshold, and I don't have 1 below the threshold. The mean cluster size, so for this thing here, well, if I am above the percolation threshold, I know that the infinite cluster size is going to be infinite. Why? Because the probability of finding an infinite cluster is strictly, that the vertex at the origin belongs to an infinite cluster is strictly positive. The probability that there exists one is infinite, so of course the mean cluster size is going to be infinite. A very long proof that I skip here is to prove that if I am subcritical, the mean cluster size is finite. That's not obvious to do. You see that close to the percolation threshold, the mean cluster size tends to infinity. And we're going to come back to that later on. Now, that's proving the first part, so that there's a phase transition. We're going to, there's a clear tendency to show that P is very close to 1/2, right? It's quite obvious, and actually we are going to see that. For that, there are a number of tricks, techniques that people use a lot that I am going to illustrate here in a few slides that are quite intuitive, and you'll see when, how we look at it. Typically, one work a lot in percolation with what's called an increasing event. So an increasing event simply means that if the open edge probability increases, that event is more likely. For example, if I take a piece of my lattice and I ask for a left-right open path crossing, so a path that connects one of the vertices on the left to one of the vertices on the right by an open path, well, if you increase the open edge probability, that event is going to be more likely. Okay? That's called an increasing event. And vice versa, a decreasing event simply means that if you increase the open edge probability, that event is less likely. typically, if you look for a closed path in that box, for example, connecting the top side to the bottom side, well, if you increase the open edge probability, it's less likely to find a closed path connecting the two because more edges are just open. And for these edges, there are interesting inequalities. For example, this one, it's called Harris of FKG inequality. So if I take two events that are increasing, so essentially I want to deal with joint occurrences of events, right? So if I take two increasing events, for example, A, the first event, is the probability of finding an open path connecting the left side of this box to the right side of this box. And B is the event that you have an open path connecting the top side of the box to the bottom side of the box. These are two increasing events. What is the probability that you find the two of them? The two are correlated because they happen on the same number of edges. And what FKG says is that they're positively correlated, which makes sense, right? Because if you know that you have a left-right crossing here in green, well, essentially you can reuse this open path that you know that exists for your top-bottom crossing. So now what you need to have is only to connect to the green path at some vertexes here and to connect from the green path to some vertex here. It's easier for having the red top-bottom crossing once you know there is a left-right crossing here. The two are positively correlated. And so you have systematically, when you have this, an inequality of that sense. Now, sometimes you would like an inequality in the other sense, in the other direction for your proof. Of course, here things are positively correlated. So what you can ask is to say, okay, if I have now the joint occurrence of two events, if instead of saying you can use, A has happened, you can reuse A for making B happen. Now I say A has happened, but you cannot use any of the edges that A has been using for its occurrence. So I close basically for the red top-bottom crossing all the edges taken by the green one. This time I make it more difficult to find a top-bottom crossing because these green edges can no longer be used, and so for the top-bottom crossing, they appear as if they were closed, right? So it makes things more difficult. And this is a situation in which both happens, in which you see that none of the two events take the same vertices. And so in this case, I have things that are negatively correlated. Essentially, the joint occurrence of the two on this joint set of edges, so that's why it's not exactly the joint occurrence, because I need to specify that on this joint set of occurrence, is less than the probability of these two occurring. It's called the BK inequality that goes in the other direction. The third tool that we use a lot is the so-called subadditive lemma. So this has nothing to do with probability itself. So it's just if you have a sequence of real number, if it is subadditive, so it means x m plus n is always less than xm plus xn. So if you have a subadditive sequence, well, then the limit exists, and it is the same as the inf of xn over n. So it's a subadditive real positive number that I will have to use here. And then xn is larger or equal than x star. And this is helpful when we study the subcritical phase for doing things like this. For example, if I want to see the probability that so I'm subcritical in this part, so P is less than the critical threshold. So the percolation probability is equal to 0. So in this case, I would like to know what is the probability that a vertex here, which I place at the origin, is connected to a vertex at distance n plus m from it. How I do that is I need to find an open path like this. Well, what I'll do is I'll do that by an intermediate step. So essentially I say, okay, among all the paths that are open and that connects this vertex 0 to vertex un plus m, there are a number who will go through vertex UM. So for example, this one, okay, goes to UM and then goes to UN plus M. And so if I look at the probability that 0 is connected to UN plus M, well, among all the paths that connect 0 to UN plus M, there are some that connect 0 to UM, and then that connect UM to UN plus M. Of course, there are others, as we saw just before, so I have something that includes this. So the probability of this occurring is larger than the probability of the joint occurrence of these two, and the joint occurrence of these two by FKG inequality is larger than the probability of the joint occurrence of the occurrence of each of them separately. That's where I use it. And so, so this is just the translation of the inclusion of the two events here in that one. And then that's FKG. And you see that this is the probability that 0 is connected to UM, and the probability that UM is connected to UN plus M for these two things. Because the lattice is translation invariant, is the same, the probability that UM is connected to UN plus M is the same if I translate everything to 0 and UM itself. And so I have the product of the connectivity function between two vertices distance of M unit and two vertices distance of N unit. And so I have this inequality here. Tm plus n is larger or equal than the product of the two. So if I take the log and I pose that xn, well, xn being this, I will have xm plus n here, xm here, xn here. I take the log, so I will have a sum here. I have a subadditive a sequence that I have just here. So by the subadditive lemma, I will converge to a limit which is just here. And so what I have is that this probability, if I go back originally, will be exponentially decreasing with a scale here given by this limit x star of p just here. And the 1 over this is called the correlation length. What I didn't show is that it is strictly positive, right? That's much more work to do, but that it is exponentially decreasing is easy to do thanks to the previous case. And actually, it's the case for all quantities, such as, for example, the radius of a cluster. So if I take the origin, and I look, this is the boundary of the box, what is the probability that the origin is connected to a vertex at the boundary of the box? It's again exponentially decreasing with size n. The cluster size distribution is again, if I take n large enough, going exponentially decreasing. So in subcritical phase, all the clusters, their size, their radius, are all exponentially decreasing with size n in the network here. That's for the subcritical phase, okay? And to show this, typically these kind of techniques, I wanted to show you just one of these proof is used to establish such quantities. In the supercritical phase, so when P is larger than PC, we know that there is at least one infinite cluster. There could be more than one. But actually, I'm skipping the proof here. There is almost surely, so with probability 1, exactly one infinite cluster. So the infinite cluster is unique. And if I look at the second largest cluster, so the one which is not the giant component, then I will have a size, the distribution of the size, which is sub-exponentially decreasing. You see that I have something that decreases not as n, but if d is equal to 2, I will have square root of n here and square root of n just here. So the second largest component is decreasing sub-exponentially with this case here. So if I go back to see where we are among the different questions, first things that we asked was, is there a non-trivial phase transition? The answer is yes. We know that this PC is between 1/3 and 2/3. In the subcritical phase, not proven here, that's long. That's the mean cluster size is finite. The tail of the distribution is exponentially decreasing. I showed that for the connectivity function. It's actually the case for all quantities, in particular the tail of the distribution. In the supercritical phase, is the infinite cluster unique? Yes. And the tail of the distribution of the second largest cluster is going to be sub-exponential. It's no longer going to be exponential, but sub-exponential. So we are left now to questions of what is the critical threshold, and if we manage to find it, what happens at the critical threshold, very close to the critical threshold just here. So what is the value of PC? And there is two steps. The first one is to show that actually PC must be larger or equal than 1/2. So we knew that it's larger or equal than 1/3. I use larger or equal to 1/2. That uses, again, the duality technique, but this time the fact that I have only one infinite cluster in the supercritical phase. I assume that essentially I am at 1/2, and I have a contradiction because I would have more than one infinite cluster if indeed 1/2 was supercritical. The next step is to show that PC is less or equal than 1/2, and I use for that again duality, but this time I assume that 1/2, since by contradiction PC must be less or equal than 1/2, I will assume that in the subcritical phase that I have exponential decay, in particular of the radius of the cluster, and show that I have a contradiction. So I assume by contradiction that the critical threshold is above 1/2. So it means that if P is less or equal, it should be an equal here than 1/2, all the properties of the subcritical phase do apply. In particular, the probability of radius, the probability that I find an open path connecting the origin to the perimeter here of a box Bn, is exponentially decreasing. That was one of the properties. So the larger here the box, well, if I take n multiplied by 2, I will have exponential of -2n times x star of p. So it's decreasing exponentially fast between the two. So what I do next is I take not exactly a box, almost a box. You see, its box is like this. I take a rectangle, so it has one unit more horizontally than vertically just here. And I'm looking for an event which is an open left-right crossing, so a crossing of finding an open path that connects this side of the rectangle to this side of the rectangle. Okay? And I suppose that the critical threshold is more than 1/2, so I'm subcritical when P is equal to 1/2. So if I look at that, okay, the rectangle that I have here is almost like this part of the complete box. So the probability that 0 connects, that the origin connects to this side here is going certainly, so if I do that for the origin, I can do that for all the vertices here. I have n+1 vertices at most here, and the probability that I have a left-right crossing is certainly less than the probability that I connect the origin to the side here of my box delta of Bn. So I have systematically that bound, and that bound I know that it is exponentially decreasing, so this tends to 0. So the probability of finding a left-right open crossing here is tending to 0 if n increases, because I am assuming that I am in the subcritical phase. Okay, so cannot find a left-right crossing with high probability if I take that too large. Now, if I cannot find a left-right crossing, I take my dual of my box, same techniques. Okay, and so if I don't have a left-right crossing, well, then it means that I can find a top-bottom close crossing, right? If I don't have a path that goes from left to right, which is open, it means every path must stop at some boundary. And so, like in this example here, I don't find a left-right crossing, so I find a top-bottom closed crossing between the two, because I don't have a left-right crossing between the two. Indeed, asking for having a left-right open crossing and a closed bottom crossing at the same time is impossible. Why? Either I have a green path, open path that connect the left to the right, but then I cannot cut it by a closed path, or I have a closed path, but then I cannot cross it with an open path. I cannot have the two at the same time. But I must have one of them, right? Because if I didn't have this top-bottom closed crossing, well, then it would mean that I would connect the left to the right by an open path. So the two events here are jointly impossible, but the union of the two is certain. So if I look at the probability that they occur, probability of the union is the probability of A plus probability of B minus the probability of the intersection, which is 0, so this is equal to 1. So that's what I have with this box here. Now, these two, the box, the blue, and the dual, they're isomorphic. I just turned them by 90 degrees to have them. So the fact that if I put the open edge probability to P, or to 1 minus P, well, it's just naming the edges, right? If I say everything closed is now open, everything which is open is now closed, I have exactly the same event occurring with the same probability. So the two probabilities here are equal if I change P to 1 minus P, because I have exactly, it's just a terminology to call them open or closed in that sentence. So if I put these two together, well, the probability of P times the n, I replace it by the probability 1 minus P of an. I have the sum of the probability that I find a left-right open crossing under open edge probability P and a left-right crossing under open edge probability minus P. The sum of the two must be equal to 1. Now I put P is equal to 1/2. Well, this is the same as this, so the probability when the open edge probability is 1/2 of crossing that box from left to right is always equal to 1/2. And what is important, we'll come back to that, you see that if I do this, that's why I find this argument really beautiful, it's valid for all n, right? If I take n very small or n very large, I have always one chance out of two to find an open edge probability, an open path connecting the left side to the right side if the open edge probability is equal to 1/2 for all value of n. So now if I put back together, I saw just before, yeah, but you know, this probability for all p less or equal than 1/2 must tend to 0. And now you tell me that whatever n exists, it's always equal to 1/2. So this is impossible. I have a contradiction. So the open edge, the probability that I have an occurring when the open edge probability is 1/2 cannot be equal to 0. So I cannot be in the subcritical phase. And so I cannot put PC strictly more than 1/2 because of that. And so it must be equal exactly to 1/2. Okay, and so that's the argument that can be played just for that. So that shows that I have just an open edge probability, which is so that the critical threshold is just equal to 1/2. But we can say more, and I'll finish on that before the break, of what happens exactly at the critical threshold. So now when the open edge probability is 1/2. By taking, again, this rectangle of size 0, n plus 1, 0, 1, n. And the exercise to go is to say, okay, imagine that you are a frog, okay, and you need to cross a little square here, of, you know, something almost square like this. Essentially, the density of water lilies on which you can go is low. And you have the choice between two ponds. One is very small, and one is very large. So if it is small, you don't have many places to start your left-right crossing, but you don't need to do a long trip. If it is large, you have many places from which you can start, but it's quite an adventure to reach the other side because it's a long trip. So which one would you choose? Well, you might be lucky, right? You might, indeed, there are not many water lilies, but you might just have 2 of them placed, you know, by chance in this little box, and then you make it here. Here, to have this occurring is much more unlikely because this must, you know, the probability of having 1 is low, the probability of having 2 is probably the square of that, but the probability of finding 20 is going to be extremely small. So there is no chance to find anything crossing this square. You might be lucky and you might be better off taking the option where you have a very small one because maybe you are lucky just at that site. If, on the other hand, the density of water lilies is very high, then you might be unlucky if you are small ponds, right? You might, you know there are many, but maybe they're just badly placed in this little square and you don't cross. If you have a large one, well, you have some spot here, but sooner or later you'll find one where you can go because the density is so high. So you're better off having many options because each of them has a very high chance of succeeding. So there is a scale, depending on the density, in which you prefer something small or something large. And so there must be an intermediate value for which you don't have any preference, which is independent of the scale. And that's precisely when, you know, you don't know which one is better than the other. That's exactly where it's scale-free, right? You don't need to have a particular scale. And you are not better in one side than the other. And that scale-free, if I don't take water lilies, but I take open edges, is when the open edge probability is 1/2. Because whatever the size of this box, whether it's small or large, you have exactly 1 chance out of 2 of crossing it for all possible scales in the settings. And so that's why it makes sense, okay, that finding a left-right crossing in this sense, it's always equal to 1/2. You have something which is scale-free here. Right? And scale-free networks, typically they are associated with power laws and so on, and that's happened just at the transition phase, and that's what we have just here. So in between the supercritical phase and the subcritical phase, I have a value here for which the fact of trying to cross this box, whether it's small or large, does not make any difference. It becomes scale-free. And what is associated with scale-free are just power laws. And indeed, we can show that the cluster size distribution is going to follow a power law. Small proof, last proof I do before the break. So if I take that, so now I'm at the critical threshold, I look at the probability, the radius function, that the origin is connected to the boundary of a box of size n. Okay, so that's the box of size n. Now, instead of taking the box centered at the origin, I will take a vertex x here. I will see a box here of size 2n, actually my rectangle of size 2n here. I have 0, 2n minus 1, 0, 2n minus, so 0, 2n here, 0, 2n minus 1. And I consider a vertex here in the middle sections, middle vertical sections that I have between the two. And I'm looking for the event that I find an open left-right crossing of this box, like the green one here, okay, connects the left side to the right side of my rectangle here. We know that this has probability 1/2 for all n. That's what we had just before. Now, if I take a box like the blue one center at x, and I look at the probability that the center of the box is connected to the boundary in blue of the box, so this vertex is connected to the boundary of the box here, well, if I was with k is equal to 0, so if I'm just here, it's the probability that the origin is connected to the boundary of a box of size n, right? It would be just, the square would be centered just here, and that's exactly this probability here. Now, a of 2n minus 1, so this green event, I can always decompose it, okay, by two events in which x here, which would be on the path at the intersection between this line here and the green path here, is connected by one side of the path to the left boundary and another side of the path to the right boundary. So the probability that I connect x to the boundary here is precisely a and k. The probability that I connect x to the left sides is a and k. And you see that I need to find two paths that do not take any vertices in common. If they were taking any vertices in common, I would move x to somewhere else. So I have the joint occurrence of these two events, and I have the union of all these events, which is larger, which is including the event of a left-right crossing. So if I place probability on that, I would have 1/2 here. The probability of the union of all these things by union bound is less than the sum of this probability. And now I have my BK inequality, the probability that I have the joint occurrence of two events that do not take on this joint set of edges is less or equal than the probability that each of them occurs separately. And since it's the same for all these vertices here, I have 2n vertices. I have 2n times this probability here, and I can take k is equal to 0. This probability being the same as beta of n, so I have this probability here, which is the same as beta of n. Beta of n, the probability that the origin is connected to vertices at distance n, the radius of distance n, is certainly larger or equal than 1 over 4n. If I take the square root, I have this probability larger than 1 over 2 square root of n. So it means that instead of having exponentially decreasing cluster radius in the subcritical phase, at the critical threshold, I have a power law, okay, just because of that. And so at the power law, the radius function behaves as a power law instead of being exponentially decreasing as before. And that's why we have also an infinite mean cluster size just at the critical threshold, and I have that also for the cluster size distribution and the mean cluster just here. Okay, so that's the consequence of having things which are scale-free and having indeed power law for cluster size distribution just at the critical threshold just here. So what have we seen? And so is finally all the questions that I wanted to address in this first part of the talk. The critical threshold is 1/2. If I am before the critical threshold, then the distributions of the cluster sizes are exponentially decreasing. If I am above, I have one infinite cluster, and the second larger clusters are sub-exponential. If I'm just at the critical threshold, the percolation probability is still equal to 0, but the distribution of the cluster radius and cluster size follows a power law instead of being just exponentially decreasing as before. And that's just the settings that we have here with some tools. You see, I wanted to show a couple of proofs, just in case one day you need to use this kind of tools. So when you have joint events, depending on what you want to show, you use the FKG or the BK inequality, plus the subadditive lemma. These are 3 of the recipes. And then the rest are constructions on the lattice, right? It's really geometric construction to do that. Some of them are extremely elegant, the one I just showed here. Some are much more complicated to obtain, but that's essentially what you arrive to. Okay, so that's all what I wanted to say for the bond percolation part, and I think, okay, I'm even 5 minutes before time. So we'll stop here, and then we move back to continuous percolation, and then how we used these tools in a wireless multi-hop network just here. So we stop here. essentially, the model that existed, so that was the first one, the Boolean model, it behaves exactly the same way as the bound percolation model with some differences. And one is that we do not know analytically this threshold, but essentially most of the properties carries over. So essentially in the subcritical phase, all these cluster size distribution are exponentially decreasing, and there is one unique giant component in the super critical phase as we have here. But things are definitely much more difficult to prove. Now, the tricks to use, I would say as engineers, when we borrow these tools from mathematicians, is the first approach that we often do is to piggyback essentially on these results. And so what we do is we try to map the model we have on a model grid of Boolean percolation. And the way to do is, for example, for grid, is to work like this. So essentially, if I have a Boolean model, right, and I want to use the grid results that I had before, well, sorry, Boolean model means essentially I have points, I have connectivity radius here, so when two balls touch each other, it means that I have a link here. So each ball here is circles a radius r/2. And essentially, to map that to a grid and reason on a grid where I have all these nice results from bound percolation, one way to do is to define three events. Essentially, you will take here a rectangle. So you divide your plane in little squares of size d/2, and you put an edge between the center of the leftmost square and the rightmost square. And vice versa, if you have vertical rectangles, is the same. You would put an edge like this, so you can define a grid. And you need to declare the edge open or closed. You are going to declare these edge open if three events occur. The first one is that you have a left-right open crossing in the Boolean model, so in the continuous model, left-right open crossing of the rectangle here from the left side to the right side. And in addition of that, you have a crossing of the first of the three little squares. You have a left-right open crossing in the Boolean model, so in the continuous model, left-right open crossing of the rectangle here from the left side to the right side. And in addition of that, you have a crossing of the first of the three little squares from top to bottom, and an open crossing from in the third one here from top to bottom. And then you say, if I have these three, my edge in the grid is going to be open. So the open edge probability is the probability of the joint occurrence of A, B1, and B2 at the same time t. And if you take the size of D sufficiently large and you are supercritical, then the probability that A occurs and the probability that B1 and B2 is the same because it's the size of the little squares are exactly the same, so the probability of the two events are the same, can be made as large as we want. And by FKG, which applies again to Boolean models, well, the probability of joint occurrence, since these are all increasing events, is larger than the probability of the separate occurrence of each of these three, that I can make as large as I want, that I can make larger than the critical probability, critical threshold of the grid that I have just here. One thing which is a little bit delicate, but that can be taken, easily taken care of, is that you see, if I have an edge xy here, my next edge is going to say yz here, is going to depend on the left-right crossing here, on the top-bottom crossing here, that is also taken into account by the first edge. So this edge and the edge which is just adjacent are depending on each other. But that's not a big deal, so we can take care of that easily, because as soon as edges are not adjacent, then essentially there is no overlap of the rectangle, and so edges are independent. So in fact, if edges are adjacent, then the probability that the edge 1 is open and that the second edge is open, again by FKG, is going to be larger than the probability that each of them is opened if they were in the dependent model. It's p squared, so it dominates an independent model, and we can use that. And then if P is larger than PC, then if the edge here is open, if the edge here is open, it means that I have this crossing, this crossing, this crossing in rectangle A, which are open. If this edge here is open, it means that I have the top-bottom long crossing of rectangle B open, this one open, and this one open. And you see, because all these crossing are open, well, it means that I have all the nodes which are on this path which are connected to each other. So essentially, if the lattice is supercritical, the Boolean model is also supercritical. And so I can reason on the lattice to make it supercritical, and then I know that my Boolean model is also going to be supercritical. So that's the way, for example, to show, we showed in the first part that there is a phase transition which is non-trivial in the lattice. If I want to show that easily in the Boolean model, that's the way to do. I would map back to the lattice. I said, oh, if P is larger than 1/2, it's supercritical. Therefore, this guy is also supercritical. And so that's the way to do easily with the different lattices of that kind. Good. Now, wireless networks, that's for the Boolean model. But we know that one of the features that we have in wireless network are interferences, and that they don't have in material sciences. So instead of saying two nodes close to each other can talk to each other, therefore are connected by an edge, and two nodes that are very far away cannot talk to each other and therefore are not connected to an edge, true. But if two nodes are close to each other but everyone around interferes with them, it's also going to destroy the edge connectivity. So a model which is a little bit more realistic is based on the signal-to-noise ratio. So essentially, we say, okay, xi, xj are the positions of the nodes in the plane. Pi is the emitting power from node I to node j. And so node j will receive the communication from node I if the signal received, which is the emitting power times the attenuation function from node I to node j, which is typically decreasing in space, often like a power law, is sufficiently large compared to the noise. And the noise is made of two terms, the background noise, which is here taken as a constant and 0, and the noise which is created by the emissions from all the other nodes k at different powers pk here, which are not the source I'm listening to, which are all the interferers here. And I put in front of this sum here a factor gamma, and gamma would be the degree or the orthogonality of my CDMA code able to cancel interferences or not. So if gamma is equal to 0, it means I can forget this. I cancel all interferences. The only noise is basically due to the background noise, and I have that situation. If gamma is equal to 1, it means I take any interfering message without processing it, and so I just add the communications from all my neighbors as noise into the system. If gamma is between 0 and 1, it means I have some processing technique that allows me to cancel some of the interferences. And so that's the model that I have. Now, two nodes I and j are directly connected. I'll take a symmetric model. If this signal-to-noise ratio is larger than some threshold beta, both from I to j and from j to I. Okay, so it's the two nodes. And that that's a model which takes into account interferences. And what was interesting to see is, what kind of graph first do you obtain with this compared to the Poisson-Boolean model? Well, first, it's a more general model, because as I said, if gamma is equal to 0, then this cancels out. And so if you cancel that out, well, you rework that equation, you erase this. So there you have the numerator is larger than beta n0 over p. I assume that, all the nodes emit with exactly the same power, so there's no power control here. I make a simplifying assumptions. Pi is the same for every node. So essentially, this is a function that decreases with the distance, so it implies that the distance must not exceed L minus 1 beta n over 0. So basically, we are back to the Boolean model. The radius of connectivity is given by this value, so it includes the Boolean model as a particular case if gamma is equal to 0, if we neglect interferences. Now, that's a realization of the Boolean model, so if gamma is equal to 0, and clearly, if gamma is non-zero, well, I destroy links. I increase the denominator, I lower the signal-to-noise ratio, so there are many links that exist here that will no longer exist if gamma is strictly positive just here. Okay, so I have something which is quite different. You have many more links here than you have links in that setting just here. But not always. Okay, so here you have something supercritical. Here also, there it was not. But if you work with other parameters on the system, even if gamma is strictly positive, you keep a graph which is connected. There are some differences, though, between the two graphs. One big difference in the analysis is that here, to define whether there is an edge or not between two nodes, you just need to look at the positions of the two nodes. You don't care about the rest, right? It's just if they are further than some radius r, there is no edge. If they are less than some radius r, there is an edge. Here, to know that there is an edge or no edge between two vertices here, of course, I need to look at the distance, but I basically need to know the position of every other node. So the edge here depends on the position of every node, and not only on the two end vertices of that link. So that, a priori, is a difficulty to cope with. So the existence of an edge depends on every other node position. And the second one is that here, I have nodes which are uniformly distributed on the square. In this case, it would be a Poisson process on the infinite plane. And so the node degree is given by a Poisson random variable. So if I look at the number of neighbors I have, well, it's the number of nodes I have in a circle of radius r. It's a Poisson random variable, of parameter lambda pi r square. That will be my number of neighbors. Here, actually, you can show relatively easily that the degree is hard bounded. Okay, so you cannot have a node degree that exceeds deterministically this quantity here. Beta is the threshold for the signal-to-noise ratio. Gamma is the gain for taking interferences. And if you look at this graph, the node degree here has a finite range. So you have degree 0, 1, 2, and so on, and maximum, the largest integer which does not go beyond 1 plus 1 over beta gamma. Whereas here, it's a Poisson random variable, so it can take any value because the domain of a Poisson random variable is unbounded. So these are two fundamental differences, I would say, between the two kinds of graph. Okay, now, if we look at this graph, if you take an attenuation function that, decrease very slowly, you might have a problem. Indeed, usually for attenuation function, a typical attenuation function in free space would be x minus alpha, so a power law of x. And theory would say that if you had no obstacles, nothing, it would be alpha minus 2. Okay, so that's the difference here. But then if you look at this term here, you sum, take one node, that would be my receiver, node J, and if I look at all the nodes that are at a distance R from node J, how many do I have between them? Well, I would have 2 pi times delta R here, that would be the surface of the annulus, times lambda nodes on average. And if I integrate, I sum all this contribution here, they will diverge. This term here will blow up to infinity. It's a paradox known as Olber's paradox for light propagation in the space. The fact that you have stars which are distributed, probably also according to a Poisson process in the space. They all emit light, so you have infinitely many of them. The propagation decreases in principle as a power law of this. And so the sum of all the contribution should diverge. So in principle, you should see daylight at least during the night. The Olber's paradox is that this does not occur. So there are other reasons in the mechanism that comes here. But so here also, if we don't impose this quantity here, then almost surely the denominator is going to go to infinity. So there is no link that can exist if we don't impose this. So a necessary condition for percolation to occur is that the attenuation function does not decrease too slowly, and in particular must decrease faster than x minus 2. If you take x minus 3, there's no problem because this integral x minus 3 x dx will be finite, and so you don't have any problem. In principle, there are obstacles and so on, so usually the measurement-based attenuation functions do vanish much faster than x minus alpha just here. Okay, so the assumptions we need to make is for sure this assumption here. This one is just that the assumptions to avoid that my degree is limited to being 1, and then I make the assumptions that it's isotropic, so there is no directional preference, continuous, strictly decreasing with the distance, as long as it is strictly positive. So it can be a finite range or infinite range, but nothing on that. And then the theorem is the following that we could establish, is that essentially there's a critical threshold, the same as the Boolean percolation, with the range that I would have without interferences, such that for any spatial density higher than this threshold, I can allow a gamma processing gain strictly positive, so I don't need to cancel all the interferences, and the graph for all value of gamma below this contains an infinite cluster almost surely, so it's supercritical almost surely. So essentially what we have in the theorem, we have a more precise shape, is that there are 2 parameters here instead of only 1. I have lambda, and I have gamma, the cancellation that I imposed on my interferences. And this is the Boolean threshold. This is the maximum value of gamma that I can have. This is the Boolean threshold here. Below the Boolean threshold, of course, interference makes things even worse. So I don't have an infinite cluster. But as soon as I'm above the Boolean threshold, then I have a setting in which I can afford to have interferences that I don't completely vanish as long as I'm sufficiently efficient for that. And a quick sketch of the proof, I'm not going to spend too much time on this one to speak more on throughput, which is more interesting, is how to deal with these 2 antagonist effects that we had in the setting. So 2 antagonist effects. The first one is like the Boolean model. The Boolean model, essentially what we want is that nodes are not too far away, because if they are very far away, of course, they are beyond the radius. And so what we do is a coupling system. So we take again, this plane that we divide in little rectangles, and we define an edge or not existing depending on the different rectangles. The first one is back to the Boolean model. So we say an event for an edge to be open is now that it is open because I have this crossing that exists, okay, in the rectangle. That's the first condition. The second one, decoupling for that, takes the other effect into account. So this first one will exist if I have many nodes in order to have this left-right crossing and the top-bottom crossings here, right? The more nodes I have, the more likely I will have this crossing. The second one, on the contrary, looks for having few nodes in the rectangle, because what I need to have is to say that for all the nodes within that rectangle, I limit the amount of interferences that I have. So the shot noise that I have, the sum of all the contribution from all the nodes here, to some amount m. So essentially, the contribution of this rectangle to the background noise is limited by a factor m over that. And I say it's open if both of them are equal to 1. One means I have my crossings, so it's populated. And second one, it's not too populated because it does not contribute to the interference term by a factor more than capital M. And so this is more likely to occur if I have few nodes. This is more likely to occur if I have all nodes. And so I need to have the two, and I take the product of these two Boolean variables to declare the edge is open or not. And then I work over that. I have my one dependent one percolation model. The first one is to say, okay, I work with the probability that this is equal to 1 or 0. I work on that, I compute this probability. I can make it arbitrarily small by sizing the rectangle D to make it large enough since I am supercritical. The second one is working on the shot noise. I skip a little bit the details here to go over that, but essentially, essentially it's just the application of a chain of bonds and shot noise theorems. And so I have also a probability of opening that I can work with by looking at this expression just here, there. And finally, if I have these two, I put the two together and I find the probability that the CA is equal to 1 or is equal to 0. I upper bound the probability that for a path of n edges, I don't go over QC over n by looking at these different parameters there. Finally, I conclude by a Pearl's argument, as I had before, by taking D large enough, that's for the Boolean model to percolate, M large enough, that's for the shot noise to take that into account. And putting all that together, I have a percolation that occurs for this setting here. These are just computations not too interesting. So the lattice model percolates, the wireless signal to interference ratio graph percolates as well. And so we have this kind of pictures. Now, this is the plot of the node density versus the parameter gamma that I can take from my interferences for this attenuation function, which would be a cubic decrease of the power with distance d. And you see the shape is a little bit like this. So essentially, this is the node density. This is the Boolean threshold, this one here. So as soon as the Boolean below the Boolean threshold, of course, there's no hope to have an infinite cluster. But as soon as you are over it, you can afford some amount of interferences. And essentially, this critical value of the gamma that you can have first increases, indeed, because you increase the node density. So if you increase the node density, well, you have more and more open path in the network. You increase the level of interference, but you first help much more to populate the area with nodes, so you can afford to have more interferences because there are still too few nodes to really have a big effect in difference terms. What helps mainly is the few nodes that you add in the network that contribute to having an infinite cluster, up to some point where suddenly, the density becomes very high. So there are lots of nodes in the plane. It's easy to connect them if there were no interferences, but they also all emit So the level of interference began to dominate. And now the second part is the part which is taking over, is the amount of interference that you have in the network, and you need to decrease the gamma, the factor that you have in the signal-to-noise ratio. You need to decrease it in order to cancel the shot noise that you have for the interferences here. So this part is essentially due to the fact that you are in the low density regime and essentially interferences are not too much of a problem. But the fact of having few nodes is actually what constrains you mainly. So as soon as you have more and more nodes, you can afford to have a worse cancellation of the interference terms in your systems. But as soon as you begin to have a high density, then your interferences are the dominating term in the denominator, and you need to decrease this parameter that comes afterwards. And actually, this threshold here decreases in 1 over lambda overall. Okay, that's for connectivity. But I think the most interesting tool to use is not so much for connectivity in this model, but for throughput. So here, essentially, what I said is to say, okay, if I have this signal-to-noise ratio, which is larger than some threshold beta, what is gamma that I can afford to have percolation? Okay, so essentially, I have a prescribed signal-to-noise ratio, and I look for the value of gamma that I can afford to have percolation. I could do the dual. I could say, okay, let me fix gamma, for example, to 1, and I decrease beta. Okay, I said, okay, I take whatever it is, and I take beta. Now, the signal-to-noise ratio is linked to Shannon capacity by a rough approximation that would claim that the Shannon capacity is 1/2 times the log n of 1 plus the signal-to-noise ratio. So the higher beta you have, the more capacity you have, the more throughput you have on your links. And so you can play in a dual way. So instead of looking at what gamma I can afford, as I did in the previous picture, I fix gamma, and I look at what beta I can have in these settings. And that's a throughput scaling that I have, that I can do. Now I'll show two ways to do. The first one without percolation, and the one with percolation. So without percolation, that gives, yeah, so there are two schools. The upper bound that I can have was known by Gupta Kumar not to exceed 1 over square root of n. So if I have n nodes on a surface, unitary surface, the throughput achievable per node with a uniform traffic matrix, so I pick an origin and a destination for every communication uniformly at random among the n nodes. The maximal throughput that I have per pair of nodes cannot scale faster than 1 over square root of n. And for the lower bounds, the approach that existed so far had the lower bound that didn't match the upper bound. That was in the order of 1 over square root of n log n. So essentially, there was a factor log n in between the lower bound for the throughput and the upper bound for the throughput that was not bridged, and that we could bridge actually with percolation. And the reason is as follows. Is essentially, I think it's the way we are educated to think about networking. You know, this is the famous IP hourglass, in which essentially layers are abstracted to other layers, right? The physical layer is abstracted to the MAC layer, which is abstracted to the routing IP layer, to the control plane, and to the application layer. And essentially, what you want to have first is connect everyone. And then once everything is connected, you look how to schedule and route communication and what throughput you can have. But you first connect everyone, you have your connectivity, and then only afterwards, in the second step, you do everything else. And what we're going to show is that this does not allow you to bridge the gap. If you want to show something which is tight, actually you need to afford some nodes to be not connected, so to get only the network supercritical, and then connect these isolated nodes, and you can then bridge the gap between the upper bound and the lower bound that you have in your setting here. So let me describe the first approach. It's simpler, and it explains why we have this throughput scaling over 1 over square root of n log n. So I have here a plane. I have n nodes in my OS network, and I need to find, I pick sources uniformly at random, n over 2 nodes in this plane, and the n over 2 other nodes will be the destinations. Okay, so how I do is I will divide the domain in little squares, squarelets, which have a size. The size Cn is square root of log n over n. So this is the size of the square. Why do I take this size? Because this ensures me that the probability that I find at least one node in every of these little square, since I have a Poisson process, is at least 1 minus the probability that the square would be empty, since I have a Poisson process of intensity n, and the size of the surface here is Cn squared. Well, if I do that, and I replace Cn by this expression, I have 1 minus 1 over square. So all these squares, if I do a union bound on this, will be populated, so we'll have at least one node with very high probability. I will not have any square here which is empty. So that's the good news. I know that I have at least one node in every one of these different squares. So what do I do next? Is I will adjust power so that a node in a square can always transmit to a node in one of the next square, so one of its 4 neighbors just around here, okay? And I do that by a time division multiple access schedule. So I have 9 equivalent classes, okay? For example, I let all the red squares here having access to the channel, and I let one node in that square talk and send information to one node to its neighbors, and I can do that in parallel times to time division multiplexing for each of them. Now, if I look at the slab, so a rectangle like this or a rectangle like this in my square, well, it has size square root of log n over n. I count now the number of nodes that I can have at most. Again, it's a simple computation in one of these slabs, and I find it has no more than this number of nodes. So if I want to schedule a communication between, say, this source and this destination, how will I do? Well, I count the number of slots I need to transmit a packet from this guy to a node in this squarelet, then to a node in this squarelet, in this one, and then in this one to reach this destination. So how many slots do I need to do? Well, I will have scheduling 1 slot for horizontal, 1 vertical, times 9 slots because I have a TDMA scheme that lets 1 square speak every 9 slots. So I have 9 slots for the TDMA. And all the nodes within a slab needs to talk. So how many slots node do I have? I have square root of log n over n. I have square root of log n over n here, square root of log n over n here. So the number of slots I need to have this communication for everyone is going to be less than 2 times 9 times 2, 36 times square root of log n over n. And so that's the number of slots I need to have. So the throughput is that I will have over that, since I need to do that for all the nodes, is going to be, if I neglect the 36 that I have just here, it's going to be per node. I will have 1 over this divided by n, so it's going to be 1 over square root of n log n here to have everyone transmit its packet to its destination when the source and the destination are taken uniformly at random here. So the scheme is relatively simple. It goes from, I find a route easily because essentially I go, Manhattan routing. I go horizontally until I go vertically to the destination. And I know I have always someone to carry traffic here. And I have enough slots so that even if I have, some squares that are populated with fewer nodes, they can carry everything within that number of slots. And that's the scheme that I have just here. Now, if the thing where I pay a price is that I need to have my square, let's here, large enough to make sure that there is at least one node in every one of them, right? I cannot afford in this scheme to have an empty square. Because if I have an empty square, suddenly I cannot transmit anything here. So this square, I need to have the square large enough so that with high probability, I have at least one node in each one of them. And that's the price I pay. I cannot go beyond that because of that. So the percolation approach takes a more radical stage. It starts a little bit the same way. But what we are going to do is to take much smaller square. So instead of having, a log n, square root of log n over n, I have just a square root of n here. So I have squares that are much smaller. And in particular, I'm not sure that every square is populated anymore because I take them too small. I just take them here. I have c over square root of n. So I have something which is constant here instead of having something which is 1 minus 1 over n squared. So I have something which is much larger. But if I take the constant c larger than square root of log n over 2, this is going to be larger than 1/2. And you remember, so again, I can put a grid on top of that, right? And declare an edge open if my little square is populated, closed if my square is not populated, and if the probability that the square is populated is strictly larger than 1/2, I know that I have an infinite cluster of open edges in my blue grid here, therefore an infinite cluster of populated square in my lattice just here. Okay, so I'll speak of square. Whenever I speak of percolation, I can take immediately the bond percolation results just by mapping this grid diagonally with edges open when there is a node inside the square, edge closed when the square here is going to be closed. And I scale things so that I have squares which are empty, but the proportion of square which are empty is less than 50%. I have more than 50% of squares which are occupied. I am super critical for the bond percolation model. So that's something which is important. Okay, so in particular, because I have an infinite cluster, there exists path that goes from left to right and top to bottom of adjacent squarelets that are not empty because I have this infinite cluster. I have this left-right, top-bottom crossing. For example, that's one of them left-right that I can use. So these ones could play the role of my slabs. The thing which is annoying is that I don't have that, well scattered. I don't have a grid. I basically have something like that. So the whole complexity of the proof is to look a little bit at the structure to know that I have enough of them, right? In the previous case, I had slabs that I could take, each of them carry traffic, and I could schedule, I could scatter, the traffic well. Here, how many of these highway do I have would be something I need to have. I call them highway because you see these will be the transportation of packets over long distance. I will need take, avoiding some empty space, exactly as, if you take a country, you have highways that are more or less scattered. You have areas like here with mountains and so on that do not have traffic, but just feed traffic to the highways. Okay, so what I'll do, I need to take C, large enough so that the open edge probability or the probability that the square is populated is larger than 1/2. Well, I'm going to increase it a little bit more. I'll keep it constant, not to make the square too high, but so that I have many crossing left to right, because the more crossing I have, the more highways I have, the more I can balance my traffic on each of these highways. And I looked at as some form of a wireless backbone, if you want, in my network that spontaneously emerges from the network just here. So how many highways? So if I pick now a rectangle of this size, that's where actually we looked in the Grimm's book, and that we found at the end of chapter 2 the lemma that saved us, which was proven by all these authors. I don't remember who they are, but in 83. That essentially says, okay, if you have an open crossing, okay, if you have one of them, and you look for having a number R edge disjoint open left-right crossing of this rectangle. That's typically something in networking we like to have, is some robustness. I know I have a left-right crossing. You know, if this fails, how many backup paths do I have? Well, there's a theorem that exists, end of chapter 2 of Grimm's books, that is this one. So essentially, they call it the interior event. So AN is existence of at least one open left-right crossing. IR is the existence of at least R edge disjoint open left-right crossing of the rectangle. And for this dimension of the rectangle, there is this lemma which relates the probability that you have this and the probability that you have this if you increase the probability, okay, from P prime to P. So if you increase, so if P is larger than P prime, that's what you pay as a factor, but that gives you the number of highways that you have in a rectangle. So if you want the questions that we have here. So we play with that, and we play also with duality, exactly as we did just before. So we say, okay, I have an open left-right crossing in that rectangle, a top-bottom of the dual crossing of the dual rectangle, which is closed. Exactly as before, the sum of the two is equal to 1. And if I switch the P prime to 1 over B prime, I have exactly the same probability. It's the same thing. Now, if I put the open top-bottom crossing, it becomes a bit complex, of the dual of the rectangle. So I find with the computation that I had just before with these values here, this kind of expression just here. I pick P prime and P, so P prime is going to be less than P over that. I pick the C square even much more than logarithm of 2. I pick it more than logarithm of 6 plus 2. And then I can make sure that the number of paths that I have is going to be larger than 1 minus C square over N. So essentially, doing this computations ensures me that I have enough in each rectangles of this size, so it has the same length as the original square, but I divide my square in different rectangles that have this width, that I have a number of highways, and the number of highways essentially scales like this, and that are all edge disjoint in each of these rectangles. So what does that allow me to have? First of all, it tells me that in my square, right, if I have my big square like this, I have divided in chunks of rectangles, and in each of these rectangles, I know that there is not only one highway, but that I have R highways that are edge disjoint from each other. Okay, I have this, and I have the same thing, of course, vertically as well. And that's what I was looking for, because essentially, I don't have, like in the full connectivity case, something which is perfectly, you know, in the full connectivity case, I have many more highways, right? I have all these highways which are perfectly aligned, so I have many more in each of the rectangle, and they are extremely flat. But here I maintain a lot of the structure, enough to have something well scattered and that I control. So in all these rectangles, I have the different highways that I can use. Here I would have 2 here, 2 here. Essentially, I can compute how many I have. It's scales as a logarithm of square root of n edges join open left right crossing. Same way for the top bottom crossing. And then I can play again the same thing with TDMS schedule. Let the floor to each squarelet, and I have 9 slots to cover all the different squares with a TDMS schedule. So 1 node per squarelet can transmit to any destination in one of the 4 neighboring squarelets just here with a rate r independent of n. So that's what I do. So I divide each rectangle, I assign for each of them a number of nodes to the first highway, a number of nodes to the second highway, and so on. And each slab, I can compute how many of these nodes. So the green one will be affected to the first highway, the blue one to the second highway here. I compute how many nodes it contains and how many slots I need to have to schedule the traffic. Well, I need 2, horizontal, vertical as before. 9, because I have 9 slots for my TDMA schedule. That's exactly the same as before. But this time, the number of nodes that I have in the slabs to be relayed is much less. Before, I had still a constant square root of n log n. Now I have no longer the log n here that I place, because compared to the previous situation, right, these highways, the slab actually, were much higher, much more broader. This was much higher than the length I have here for each of the slab. So I had highways which were very wide, okay? But essentially, I needed a lot of slots to schedule everyone on these highways. Here, I have much less traffic on each of the highways here. And so I need a number of slots which is much reduced compared to the previous case. So the highway rate this time is no longer 1 over square root of n log n, but 1 over square root of n. And so that's the good thing of that. Now, not every node is on the highway. Okay, I have still nodes that live in the countryside that are far from the highway. But I have few of these nodes. It's exactly, if you think of it, it's a little bit how, you take any European country, how it emerged, right? It has a backbone of highway that goes in the, usually close to the densely populated area. And then you have some countryside with some villages that are a bit far from the highway, but with few inhabitants. And so these ones, well, I will add 2 more slots. One for bringing just fresh traffic to the highway. These guys do not relay any traffic. They just send traffic. This guy relay traffic for others and their own traffic. This one just send the traffic. It goes on the highway, and then it arrives to the destination, which might also be in the countryside. But then you have just 1 slot for the draining phase. And since there are very few of these nodes, you can do long hops simply because you don't have much interferences. There are very few of these communications. And so again, it's a little bit more communication for that. But since you have fresh traffic only, you can do longer hops and you take the relay. So you drain to the highway, you go horizontally, then vertically to another highway, which I didn't draw here. I mean, it was enough to go over there. And then you drain to the destination just here. And that allows you to achieve a rate which is only of 1 over square root of n and no longer a rate over 1 over square root of n log n. Okay? So this would be a simulation of the typical size shape of the different highways you would get. So you see, okay, here you have highways. You have a number of them. It's only the horizontal one that we draw. And each of them relay traffic. So essentially, we divide the square here in slabs, and we assign traffic to each of the highways for the different slabs. We know that the highways are sufficiently well scattered to relay traffic with the number of slots we have allocated in the schedule, which doesn't scale more than square of n, so 1 over square of n is achievable as a rate on the different highways. So if I compare the situation, of course, I cannot operate the network in the subcritical phase, because there I don't have any highway, right? They all stop at some point. So there is no left-right crossing, and I cannot do anything useful here. If I have something fully connected, it's great. I have a very dense network of highways, but they interfere so much with each other, right? I need to make the power so high to connect everyone that I cannot relay. I need a lot of slots to push the traffic through the different highways. And if I am in the supercritical phase of a percolation model, then if I look at this, well, I have highways, much fewer than here, but I have enough highways that goes from left to right. And I have also enough highways in each portion of the rectangles to transmit traffic. And then for those guys, okay, which are the little blue isolated clusters, well, they are not on any highway, but they will not relay any traffic. They are isolated, they just send their traffic, or they just retrieve traffic to the different highways, and doing this is the optimal way of operating if you just look at scheduling. Of course, there's complexity if you want to do that in practice, but it's scheduling. And if you think of how, so not taking communication, wireless network traffic, but human traffic, if it's very close to the way the transport, the highways and secondary road network is organized in a country, right? You naturally have some areas which are of high density. You have a highway crossing them. You have remote villages that will just send traffic to these highways, and naturally that's spontaneously the way how traffic emerges. It turns out that to prove that this is optimal for wireless network, at least order optimal in wireless network, that's exactly the way to go also for this setting. So if I look a little bit the pictures that I had for connectivity, that's for the Boolean model, if I neglect interferences. And if I have interferences, I have this kind of plots. And so the gamma was decreasing as 1 over n. This is the Boolean threshold. If I rescale that for n nodes on a finite domain, I would scale that as 1 over square root of n. So the typical way in which I have full connectivity is to assume a radius connectivity range that scales as square root of log n over n. And that's clearly not optimal. I could afford something which is much better if I scale things as 1 over square root of n, because then essentially I can combat interferences. I can allow interferences much better to have here in this regime, and that's the optimal regime that I need to have. And you see also that the tools we use are really the band percolation tools, right? So the techniques in terms of technicality, if you had to prove, is to say, okay, I have this wireless network. I map that on a grid, okay, to have something like this. And I reason on the grid with band percolation results. And at the end, the results themselves go back in the domain I have just here. The only thing which is not percolation in this setting, all this is percolation, is this. Essentially to say, oh, now I need to let, to find an access, a multiple access scheme in which I let one node in every little square talk to each other. How should I organize this in order that the signal to noise ratio is high enough for each of them for communicating that? I have 9 equivalent classes. It's the same for full connectivity or not, except that here the little squares are much lower, and that's the only place here. But it's just a token that I gave from one node in each of the square, one after the other, and that's the only place, and that doesn't scale with n or anything like that. So everything else is just purely a percolation result that come into play, with a result that is not very important maybe for mathematicians, but which is probably very useful for us. Which is this result here. Well, which is this inequality that relates for two different open square or open edge probability in the Boolean model, the probability of finding R edge disjoint open crossing of the rectangle with the probability of having one crossing. So that's typically the kind of results we look for when we have robustness in the setting here. Well, so that's how I wanted to show. I skipped a little bit some technical details for the sake of time. So in particular, how to adjust all the constants, which is a bit tedious, but not very important, to give a little bit the spirit of how we used the different results for throughput scaling and for connectivity of wireless network. Now, to conclude, so I don't have a simulation, an exercise session, a notebook, but rather a few questions to see the insight that you would have in using percolation in different settings. So, voilà. So a few questions that would have, since, so I coined that yesterday because I didn't know we had to do some exercise. So we handled, so first a few questions about band percolation. So in band percolation, what we saw is that for 2 dimensions, so the lattice square, there is a non-trivial phase transition. We showed that the threshold was between 1/3 and 2/3, that's using Pearl's argument. And much more complex, we gave some elements showing that actually PC is exactly equal to 1/2. So this is easy to show. This is much more work, but we have to do. So the question is, what happens for d is equal to 1 and d is equal to 3? So for d is equal to 1, what is do you know what the critical percolation threshold is? So it's 1/2 for d is equal to 2. So for d is equal to, yes? One. Exactly. Exactly. So if you are in one dimension, well, the only way to connect to infinitely vertices on one side is that this edge is open, the next one is open, so I connect to distance n with probability p to the n tend to infinity, it's 0. So in d is equal to 1, there is no non-trivial phase transition, and the threshold is equal to 1. So essentially, it's a trivial case here. For d is equal to 3, okay, I tell you immediately, what is PC? If you find that, don't tell it here. Publish a paper, because you'll be certainly worth it. This is a very complex case to do. But how to show that there is a non-trivial phase transition? Exactly the same counting argument as we did before. So what we can do, that's what we did for L2. Okay, for L2, you say I count the number of self-vibrating walk of length n, and what I do is I have 4 edges that I can take for my first step, and then for all the other steps, there's never more than 3 choices that I can do, sometimes less, sometimes 2. And then when I do that, I count the number of open paths. It's less than the average number of open paths, which is simply the number of self-vibrating walks that I can do, and the probability that all the edges on the self-vibrating mode are open. So if I am in dimension 3, what do you think so here we could have a lower bound, which is 1/3. If you are in dimension 3, what this technique would give you as a lower bound? Yeah. But it's not zero. So if you think of it, if you start from 0, you have now 1, 2, 3, 4, 5, 6. Okay, so the 4 becomes a 6. And then each of them, you cannot go back the same, so you have no more than 5. So if you redo the whole thing, you will have here 6 times 5 and minus 1. So for sure, it's going to be larger than 1/5. Okay, so you just do the same thing here. And so the percolation threshold is going to be 1/5. That's for the lower bound. Why is it so difficult for 3 dimension? Because for the upper bound, we use this argument, which is Pearl's argument, right? I look circuits, and then I count everything, and it was fine. Now again, if you find how to do that in 3 dimensions, please tell me. I'm happy to co-author a paper on this. It will make me fast. This argument works in 2 dimensions. You cannot in 3 dimensions, you don't have a self-dual, you don't have this kind of property. So this doesn't work, unfortunately, in 3 dimensions or in 4 dimensions or anything on that, right? The Pearl's argument, you lose it. It's only proper to 2. But you can still find an upper bound on the percolation threshold. So do you think it's easier to find an infinite cluster in 3 dimensions or in 2 dimensions? Yeah, in 3. You have many more paths, vertices that you have. So indeed, if in 2 dimensions you have an infinite cluster, you just add edges open or closed on that, you still have an infinite cluster there, right? So what you can do, of course you cannot use that, but for sure, so it's larger than 1/5, and it's less than 1/2. So it's in between the 2. And indeed, the higher you go with the dimension, the more you will go to the left for the threshold. But computing it exactly is definitely open. And one of the reasons is that we played a lot with duality. And so the question was at the beginning, why do we need the duality? Well, I mean, without duality in these schemes, we lose a lot. And so it's difficult to show things on that settings. The second exercise, it's more qualitative. So it's something that we had as a question, is if you think of, okay, I think now of hybrid networks as something which is multi-hop, but also you have a few access points that are connected to a wired network. So for example, in 1D, okay, these nodes can connect to each other, but at distance L, I place a fixed antenna. And so the node can connect to the antenna, then, it's connect to the wire, so I can connect to this diametrically, but I need to connect to all of these guys. So I place a base station every L space unit in 1D, or, every distance L from each other if I am on 2D. And, okay, the practical question is, where did I put my, here? Okay, I take 2 areas of Switzerland. Okay, one is Zurich, and this is proportional to the population density here. And the other one is the Surselva Valley in Graubünden, which is this valley here. And I wonder, where do you think is the most useful of the 2? Okay, so if you have the choice, say, I don't know, you're a Swisscom, you have some budget, you need to deploy this. Are you going to deploy this? I mean, by default, you would deploy this first. I just speak of connectivity. I don't speak of throughput something. Okay, in Swiss Roman, we say, oh, of course, they all go for Zurich first, right? That's the default assumption. But using this, where do you think it helps the most? So if I place a base station here, every L unit, or I place a station here, every L unit. Of course, it helps in both cases. but in which there's one case where it will help drastically more than the other for long distance communication. So imagine you have, you know, a kid here calling his grandfather here, in which case it's going to be more useful to have the hybrid network than the other.
So the measure is that everybody has to be connected within this.
Exactly, exactly. Yes? Yeah. Exactly. So what happens is that here we are almost something one-dimensional, right? So for which we don't have percolation except if it's full connectivity. Here it's something which is fairly two-dimensional, right? You have, it's not Poisson, because we have clearly, but it's two-dimensional and it's well scattered on the landscape. So here, if you look, if you increase the radius of connectivity, you will see suddenly a giant component that emerges. So most nodes will be in that component, even if you don't have a hybrid network. Here, until you have connected everyone, you will not have a giant component to have. So if you increase the radius, you will have large clusters, but unfortunately little gaps between them. If you place a hybrid network, while you have an antenna in all these large clusters, they will help a lot because they will carry the traffic long distance. Here they will help, but anyway, you have already path between the different nodes. So the picture will be like this. In this, in this scenario, you see that without the hybrid network, you have this phase transition that occurs. So that's computed. It's a probability that a node is connected so it's a fraction of nodes that are connected to each other here. You see it goes from 0 very rapidly to something very high. And so it helps, of course, but still the probability is not that high if you have a hybrid network. So the distance between, I don't remember which they were, but much larger than the radius that we have here. And then when connectivity in the supercritical phase, they don't help at all for the connectivity. If I take this scenario here, you are always subcritical if you just have ad hoc. If you add antenna, well, since you have clusters that will become very large, they will connect many nodes, and in this case, connectivity will be ensured by just a few additional antennas there, right? So the difference between the two, just in terms of connectivity, is completely explained by percolation. So that's why, even though here we can only compute things numerically, it helps understanding why we have this phenomenon occurring. And even if you look, okay, I didn't bring the picture here, but we did a student project here. So even if you take Zurich region, you see two thresholds. The first one, so it goes like this, and then like this. The first one is the city of Zurich that percolates. And the second one is the canton of Zurich that percolates. So it's two different densities that occurs. So you have first this one, you have quite a large number of people connected, and then the second one is basically for the rest of the canton that occurs. And then final exercise, there are other structures for which it's easier to compute percolation. And one would be a tree, and let's take a binary tree to have that that occurs. So here, what I have is I have a root. Okay, I have the binary tree here, and exactly as in the lattice model, I have a bound percolation model. So I kill an edge with probability p, with probability 1 minus p. I keep it with probability little p. So in this case, what is the critical threshold? Now this requires some computation, but it's much easier than in the previous case, because this is actually a Galton-Watson branching process, for those you have seen. So essentially what you see is that if I start from 0, I can view that as the ancestors. These are its two children. If the edge is open, means the child is born. If the edge is close, it means the child is never born. And so I disconnect the whole descendants here. And so I have a Galton-Watson process, and this Galton-Watson process I can analyze using Markov chains. Okay, I can say, well, the probability that I have an infinite cluster is 1 minus the probability that these processes stop at some point. If these processes stop at some point, so it starts from one ancestors, and at some generation L, I don't have any individual left in the setting. And this I can compute. It's the hitting time of a Markov chain. So I start a Markov chain from 1, and I compute the probability that it reaches the state 0. As soon as there is 0 person at some stage, I don't go. And I can compute that easily. The expression is this one, H10 is the sum of the probability of transiting from 1 to I, so the probability of having I children from one individual, times the probability that starting from I individual, I reach state 0, which is the same, since the Markov chains are independent, of the probability that from one individual I reach state 0 to the ith power. So if I compute this, well, here, the probability of having children, I can have 0 children if both edges are closed. So this occurs with probability 1 minus p squared. I can have 1 edges if one edge is closed and the other one edge is closed, the other one is open, and I have 2 edges, so I have 2 times this possibility. And I have 2 children from one edge if both edges are open, which occurs with probability p squared. So I replace these probabilities here by this expression here, and I have these polynomial equations that I need to solve. I need to find the minimal solution of that solution, and the minimal solution is equal to 1 if p is less than 1/2. So the percolation probability is 0 if p is less than 1/2, and is equal to this quantity, if I solve this equation, if p is more than 1/2. So here I compute exactly the percolation probability. It's a very simple case. I can compute theta of p exactly. So identically just here, and I have exactly the results. So this is the percolation probability that I have. 0 if p is less or equal than 1/2, and something strictly positive if p is strictly more than 1/2. And you observe something which is interesting, is that the threshold is again 1/2 for the binary tree, exactly as the lattice, although it's 2 completely different topologies that you have, just by chance that it happens this way. But you have, for many exponents in percolation, some laws that seem to be universal. So essentially, independent of the topologies, you find the same values. Not for the critical threshold, but for example, a relation that link the decrease of the radius, cluster size distribution, and so on, that look to be a universal solution. But so you could view the binary tree actually as a particular case of percolation that is completely workable, right? Now, of course, here the fact is that since you have a tree, you don't have any loop in the system, so it's very easy to analyze using classical Markov chain, but you have exactly the same phenomenon as just here. Okay? Good. So since I'm the only thing, if there's no question, we can stop here. So this afternoon, there's not single probability anymore. So if you're tired of probability, everything will be deterministic, completely different from this afternoon. Thank you very much. Exactly. But it's a quite different chapter. So I'll give a short introduction, actually. So that's why essentially following the book that we wrote together with Jean-Yves Le Boudec. So Jean-Yves Le Boudec has also, there's also a longer tutorial of, I think, 2.5 hours that you can find on YouTube And so this is only, I would say, the first part, maybe a few differences with it. And he has more recent work, because I have not worked on this for quite a few years after the book. But so what we are going to see is essentially the fundamental concepts of network calculus. So here, there is no probability at all, contrary to the first 3 hours. So everything is deterministic. And so the first thing would be to see a little bit what is network calculus. So here, we advertise our own book. But essentially, you find it online, and Jean-Yves maintains an update of all the typos and new things on this web page here. There are two fundamental concepts, one that describes traffic and one that describes systems. Traffic is described in network calculus by what we call arrival curves, and systems by service curves. And when you have these two, you can actually look at, again, performance analysis, but here we have, I would say, traditional metrics for performance analysis. The two main ones that we care the most about, of course, is backlog and delay, and we'll have bounds that are deterministic bounds. So essentially, for any traffic conforming to an arrival curve and any elements that offer a service described by a service curve. We'll see then shapers. I'll just mention the packetizer. There is much more on that in Jean-Yves' tutorial if you're interested by that. And then I'll finish, I would say, by something, okay, it would be too much for an exercise, but more like a case study, how we model and we apply network calculus to compute the minimal playback delay and look ahead, if you have look ahead possibility, for video smoothing and streaming in such a system. Okay, so what is network calculus? So network calculus, you'll see why we call it calculus, but essentially it's the deterministic analysis of queuing and flow systems arising. Initially it was in communication networks. Now I would say there's a larger class of networks that offers guarantees that you can prove strictly, so formally. So what is important to have is to have provable guarantees. That's the goal. And what it relies on is tropical algebra, typically min plus, also max plus, but here I'll describe only min plus algebra. So it's an algebraic framework. You'll see different from the framework, the algebraic framework which we're used to, and that we need to operate to analyze these queuing systems. It was developed, I would say the first big names is René Cruz, who this is probably one, I think it's probably the first papers that look at calculus for network delay. That has a rival curve, service curve, and these concepts then. And then there were two, I don't know, okay, it comes back. Yeah, probably. Then two books that appear at the same time, the one of C.S. Chang, but I don't know if this, okay, maybe it's probably the cable somewhere. This morning it didn't have any, okay, hopefully it works. And then there are more recent textbooks. I should mention the one of Anne Bouillard and her co-author that has many new results, in particular on FIFO system and round-robin, various versions of round-robin schedules in much more complex systems. Okay, so in terms of use cases, I would say it has revived a lot right now with the advent of deterministic networking, and typically for 5G industrial automation. Actually, this is, yeah, if it comes every 5 minutes, this is far from deterministic. I should go back to probability. So with the advent of industrial automations and working groups, like the time-sensitive networking working group of IEEE, or in the IETF deterministic networking group that essentially look for, and this group did not exist, of course, 20 years ago. One case study as I was mentioning this morning, is in avionics, of course, when you need to have provable guarantees. And essentially, the network, the full duplex switch Ethernet network that is deployed in the A380 Airbus essentially combines network calculus with algorithm optimization algorithm, essentially for checking a lot of priorities. There are more than 1,000 checks to do, and so essentially you reduce the search space by applying a network calculus. Another area where it applies also is, I would say, VLSI systems, so networks on chips, and that's the other area. I would say there is a lot of work done under the name of real-time calculus by Lothar Thiel and his team at ETH. It's fairly close to network calculus, modulo a few differences. Like typically here, we are going to work only with minimal service curve. We're interested in pushing packets as soon as possible. Maximal would be not earlier than some deadline, and that's something that they use in real-time calculus. Also, our functions are in general for us starting at time 0, so we consider only times to be positive, which is not the case in real-time calculus. What I will not touch upon is the stochastic version of network calculus. First, because I promised to do no longer probability, but second, because that's still research to be made. So essentially, deterministic network calculus is fairly, at least what I will show here is fairly stable. So there is research on more complex systems and more complex scheduling schemes, but essentially the bounds are tight, so you cannot improve them under the systems. With stochastic network calculus, there are different frameworks, and there essentially the difficulty is either you give very strong guarantees, but basically they boil down to almost something deterministic. So essentially you don't have the strength of deterministic, but because you allow probability, but at the end it boils down to that. Or they're too loose, so it's difficult to find the right framework for stochastic network calculus. Often it's combined, I would say, with large deviation theory in this setting, but that's a more open research area, even though there are many things that have been done. I think one of the promising avenues is when you have only one ingredient, which is stochastic. For example, if you have different flows that arrive periodically, but you have, so the period is deterministic, but the time at which they arrive might be stochastic to start first. So essentially you have different sequences. That's the kind of things that can do. I should also mention that since then there are lots of software tools that have emerged, so by many of the authors I presented here. Here are a few of these software tools. Often they are in Python. There might be also a few industrial ones that, but I'm not sure that they include systematically a network calculus in them that exist, and so I think most of these are open source. Okay, what is network calculus? The way I view it, so that's because I am an electrical engineer by education, is that I learned in the university in the signal circuits and systems class this kind of circuits. Essentially in these circuits I have an input signals, which is a voltage here, an output signal, which is again a voltage, and then here I have an RC cell with a resistor capacitor with an impulse response beta of t, and essentially this signal is filtered by the impulse, the filter with an impulse response beta of t, and what I do is I multiply these two, so I take this one, I translate it and I flip it in time, I multiply it by the entry, and I add them to get the output signals. And so that's something we do in conventional algebra. Well, if you take a very simple queuing system, so you just have traffic arriving in a buffer, which here we will take infinite, and delivered at a bit rate which is equal to, say, to get the output. Well, if you write this, essentially x of t, instead of looking at the instantaneous rate, you take the cumulative amount of traffic that has arrived in 0t. So x of t is the total number of bits that have arrived between 0 and t into the system. And y of t, similarly, is the amount of bit that has left the system between 0 and t. Then, essentially, the impulse response would be a feature of the system, and the impulse response here is simply c times t. It's the maximum amount of data that you can exit in an interval of length t from the system, since you have a pipe here limited at a bit rate c. And the output, you can write it this way. And you see that it resembles a lot the previous expression, because you take the input x of s, you take what we are going to call a service curve, but essentially what would be the impulse response of the system, you shift it and you flip it, you add the two instead of multiplying the two, and you take the minimum over all possible s between 0 and t, take the infimum here because it's in continuous time, and you get the output, instead of doing the integral and the sum here. But if you look at the two, if you allow me to replace the integral by the infimum and the multiplication by an addition, I get essentially the same operation. And this is actually called a min plus convolution of the input signal and the impulse response of the system that we're going to see here. I could view that also in max plus algebra simply by counting the time at which I have received different cells, and then I would have a max plus equation, but I'm not going to speak too much of that. So essentially, for me, looking at it from a perspective on electrical engineering, it's another linear system theory. So the algebra we are all used to is, R endowed with addition and multiplication. It's a ring, so it has all the property of, commutativity, associativity, distributivity, and so on. For example, this is distributivity of addition with respect to multiplication. Well, the mental exercise to do is to change the addition by a minimum or an infimum and the multiplication by an addition. So this time, I replace the multiplication by an addition, and I replace the addition by the minimum. And if you look at this, A plus the minimum of B and C is the same as the minimum between A plus B and A plus C. And actually, all the properties that you have, commutativity, associativity, distributivity, carry over. Okay, it's like in Asterix. No, there is one that resists, and you'll see that it makes, it will make a big difference, is that for addition here, if I give you A, you will tell me minus A will give me the neutral for addition. But here, the addition is replaced by the minimum. If I give you A, there's no element that gives the neutral for the minimum. The neutral for the minimum is infinity, so essentially I should say that R is extended union infinity here to have the neutral element in the set, but I cannot have a neutral. What I can offer instead is isotonicity. So A, minimum A is equal to A for any A. You don't have that, but that actually is much weaker than the other. So this defines a ring. This will define a so-called dioid. So it has one rule, which is isotonicity in addition, extra, but you lose the fact that you don't have an element for addition that gives you the neutral. And that has a consequence. It's a much weaker algebra. You can do much fewer things because of that. So it's an annoying thing. You have the same thing for the max plus algebra that we are not going to use here too often, but that is also sometimes used in calculus. Okay, so what are the important concepts? Well, there are two things. One is to characterize traffic, and we do that with the concept of arrival curve. And the other one is to characterize the elements of the system thanks to service curve. Now, what is powerful here is that you remember that if you had an electric circuit, you take some little filters of first order, as I showed. You combine them, you have maybe a very complex electronic filters. As long as it is linear, you can compose the convolution of all the impulse response, give you the impulse response of the total system. And so essentially, you can analyze that as a black box, treating an entry, processing it to give an output. So it's very efficient. Even if the thing looks complex, you don't need to write the detailed equations. You have these tools that are very convenient. You are going to see that it's exactly the same here too. So you might have something fairly complex for each of these systems here, not a CBR, a constant bit rate at the output, but something more complex. And then we are going to be able, in some cases, to combine that efficiently, especially if we have a single flow. If we have background traffic, things are much more complex, and that's the topic of much research nowadays. But if you have single flow, it's going to be extremely easy to combine this. But first, we need to characterize a little bit the traffic before going the service curve. So the first part will be to go over these arrival curve. Okay, so the trick in network calculus is that you always take cumulative values for flows. So if I have a flow, okay, if I have a fluid model, packet model, sometimes I use, but we are not going to use that, the discrete model. So if I have fluid models, well, I start here always with something that is 0, and then as the fluid, the units of data arrive in the system, the rate at which it arrives here would be a rate which is constant, then nothing arrives, then it arrives a bit more, and what I take the flow here is always a non-decreasing function because you just keep accumulating traffic. You might be flat, but you just increase that way. So it's non-decreasing. And by convention here, we start at 0, so we don't have anything before time 0. And so capital F will be the set of this function. It can be continuous in a fluid model, or it can be non-continuous if I have packets, right? If I have a packet, the first packet arrives at time 1, and it has this number of bits. The second packets arrive at time 5, it has this number of bits. At time 5 by 5, I have the third one that has this number of bits. I have this staircase function. The convention is to take it left continuous. So essentially to think that the packet has not arrived yet completely at time 1, it has arrived just after time 1. You could do that maybe right continuous, but you need to be consistent, of course, to keep all the time the same continuity between the two. You might also have discrete time model. For example, you have cells, but that's much more rarely used. So for example, if I take an MPEG file, this is the bit rate that I have for the different frame numbers. That's the integral of this R that I would have, and if frames are delivered at periodic times, well, this is R of t if I map the frame number onto times that I have just here. And you see here that R is increasing slowly, and then here I have a big burst of data, so the rate increases a bit more, and so forth if I have this file here. So that's the input flow, okay? And then the output flow is exactly the same. It's the amount of bits that has left the system, R star of t, that I have just here, in the fluid model or in the packetized, in the packet model. And the two metric of interest for us is essentially the difference, the vertical difference between these two, that tells me in the system at that time t, R of t unit of fluid have arrived, and R star of t has left. Therefore, the backlog in the instantaneous backlog in the system is precisely this vertical distance that I have just here. And vice versa, if I look at the horizontal distance, well, if data are served in the order in which they arrived, well, it means that all the data that has arrived here before exiting, will need to wait this amount of time before they actually leave the system. So the graphical interpretation is quite simple. Backlog are the vertical distances between input and output cumulative traffic curves, and horizontal distance are the delays that every unit would have before entering and exiting the system. Now, what is an arrival curve? So if I want to have guarantees on my traffic, I need to work with traffic that does not exceed, that doesn't come infinitely fast into my system. And the way to define that is with an arrival curve. And that's the definition of an arrival curve. So essentially, I have my cumulative flow. So if I take R of t minus R of s, that's the amount of traffic that has arrived between time s and time t in the system. And I say it satisfied an arrival curve if for any s less than t, this is less than some envelope alpha of t minus s. Okay, so this is the arrival curve. So for example, if I have this arrival curve, which is a typical arrival curve that I have, and I denote it by gamma RB, two parameters, the slope R and B, which is the burst that I allow. So essentially, it means that I can have, so the function is left continuous, right? It's 0. Then it jumps to B, and after B, I can accept data at a rate equal to R. And so it means this R conforms to this arrival curve if at any point that I can find, it's always below that curve here, right? So I allow a burst of B, I allow the traffic to arrive at rate R. If it stops a little bit, then I allow again some portion of a burst, and essentially I control traffic using this, this kind of a fine arrival curve, right, with two parameters. I could have another one, for example, this staircase arrival curve. So there I have a periodic arrival curve, but I have some slack, little tau, which is a tolerance that I have. So it's for flows that are periodic streams of packet of same size. So each time I get a packet or a cell of cell k, which is periodic except that there might be some variable delay here. And that could be a system in which I have this arrival curve, right? So if, for example, here, my output flow will conform to this arrival curve if I start with an input flow which is t periodic. So if R is t periodic, it means that the amount of traffic that I can have between U and t will be the number of cells I have over the time interval. So I take the integer value between the length of the interval divided by the period multiplied by k. And then I can have some tolerance tau. So it means that what I have at the output, R star of s, must be larger or equal than all what has arrived minus tau. So I might have some delay tau. And vice versa, R star of t minus R star of s, where R star of t cannot be more than R of t, right? That's the amount of traffic that has exited the system at time t. That's the amount of traffic that has arrived in the system until time t. And R star of s is larger than this. So if I put a minus sign, I have this. And this, again, since I have a periodic flow, I get this, which is the arrival curve here. So it's a stair arrival curve that I have here. Okay, now, I can have a flow if I compute properly the rate R and the burst B that conforms to both arrival curve. Because if R is large enough here, k over t, and B is large enough, well, I can have a periodic, quasi-periodic flow that conforms to this arrival curve. The arrival curve is not unique. I can have multiple arrival curves here. This affine arrival curve, the most frequent one, it's called a leaky bucket controller because essentially it's as if you let the flow go in as long as you can feed a bucket here. The bucket empties of water at rate R and has depth equal to B. And as long as you can accept the same amount of traffic as water into that bucket, you let it go. As soon as the bucket is full, you stop the traffic from going. So that's why it's called a leaky bucket system. A standard arrival curve, for example, that was defined in RSVP is the minimum of 2 leaky buckets. One leaky bucket with a peak rate and a small size, which is the maximal size of a packet, and then a sustainable rate, which is smaller, and a larger burst, which is this one. And this was the arrival curve that you have for leaky buckets. Now, I can have multiple arrival curves. What might be the most interesting is to have the smallest of the arrival curve. Why? Because if I have an envelope which is small, I probably can derive tight bounds. So if I have an arrival curve alpha, how can I compute the minimal arrival curve? And there is a way to do that systematically, is basically by computing what's called its sub-additive closure. So if this was an arrival curve, the sub-additive closure, sorry, I forgot to put a bar here, is this arrival curve, and that's actually an arrival curve also for this flow here. So how to do that? I need to introduce, again, this min plus convolution. So min plus convolution of two functions, white sense increasing function, is this operation here. So I take one of the function, I flip it, I add the other one, and I take the minimum value of the two, and I get the min plus convolution, which I denote by this side between the two functions here. So to do an example, let's suppose that we have f of t here, g of t here. What I do for f convolve with g, well, I take the first one, f of s, I take this time t at which I want to evaluate the convolution of f by g. I take the second one, I shift it to t, and I flip it. I add the two, and I take the minimum value. And this point here will be the value of f convolved by j. And if I do that for all time t between these two functions, I get this curve here would be the min plus convolution by itself. If I take a function f of t, and I convolve it by itself, I can do the same. I take f of s, f of t minus s, I convolve the two, and that will give me the value at time t. I report that, and so that would be f convolved with f for the same. And so convolution is helpful because we can express arrival curve with min plus convolution. Remember that for an arrival curve, it means that for any time frame going from s to t, the amount of traffic flowing on the link, characterized by this arrival curve, is upper bounded by alpha, the arrival curve evaluated in t minus s. So if I rewrite this, okay, I move x of s to the right-hand side. I have this expression here, and this must be true for all s between 0 and t. So in particular, it must be true for the s that achieves the infimum of this expression, and the infimum of this expression, that's precisely the min plus convolution. So x less or equal than x convolved with alpha is equivalent to say x conforms to the arrival curve alpha. Okay, so that's exactly equivalent because you can go from one to the other exactly this way. Not yet with subadditive function. So subadditive function, that's the only thing which is in common with what we have seen this morning. Essentially, I have function, so convex and concave, that I think is something we know. Subadditive simply means that f of t plus f of s is larger or equal than f of t plus s. And if I have a concave function that passes through the origin, it is automatically subadditive. But if it is subadditive, sorry, this bar should be here. If f is subadditive, it is not necessarily concave. So concave function passing through the origin are subadditive, but subadditive function is a larger class. If two functions are subadditive passing to the origin, their convolution is also subadditive. So for example, this function here is concave, it is subadditive. This function here is not concave, but you can check that it is subadditive also. This function is convex, and this function is again convex. Both of them are convex, and these are two functions that are convex. If I take the convolution of this function by itself, so this is some of them, as this will be subadditive, this will not be subadditive, and you'll see that the closure is going to be different for each of them. So some properties of min plus convolution, it's closed. So f convolved by G is always in the set F of wide sense increasing function, associative, commutative. It has a neutral element. The neutral element is basically, this function, but with a delay equal to 0. Indeed, if I have the function that is equal to 0 at time 0 and infinite elsewhere, well, the minimum between f of t minus s plus delta 0 of s is reached in s is equal to 0 and is equal to f of t. So that's the the neutral element. Convolution is distributive with respect to what plays the role of addition in this algebra, which is the minimum. It's isotone. And there are some rules, you see, that will allow you to compute min plus convolution in a much easier way. I would say that's the calculus part of network calculus. Typically, if you have functions that pass through the origin, as we have here most of the time, the min plus convolution of two functions is going to be the minimum of the two functions. So it's easy to do. The concave, is less or equal. If they are concave, then it's going to be the minimum of the two functions here. And if they are convex but piecewise linear, as in the example I have, well, how to obtain the convolution is simply by putting the different segments composing that function in increasing order of slope, so sorted by increasing slope. So for example, if I take these two convex functions, and I want to compute the min plus convolution of these two functions, both are convex and piecewise linear. Therefore, I have three piecewise linear elements here. The one with the shortest slope is this one, then this one, and this one goes to infinity. So this one actually would be rejected to infinity, will never appear. And so if I do the convolution of these two, I will have a delay t, which I will call a latency, and a slope which is equal to r here. So the convolution of this function by this one will give me this. This is something that we are going to use very often as a service curve, a rate latency function that we are going to do later on. So if I use the rules, I am going to go much faster to compute this convolution. For example, if I do the convolution of these two, you know, this one is convex or concave, is both convex and concave passing to the origin. This one is essentially a constant k plus a rate latency function, which I can write this way. Well, I can play with all these rules, a little bit like calculus. I use the fact that I have distributivity with respect to multiplication, that I have associativity, that the min plus convolution of two concave functions passing to the origin is the minimum between the two, that essentially these are two convex functions, so I put the slope, which is the lowest before the other one, so I get this one, or I have two concave functions, and so I take the minimum of the two, and at the end of the day, I arrive to this result here by just playing rules like that. This is what takes a little bit of time of gymnastics to do, but it's playing with all these rules of algebra, essentially to compute this convolution, and it can be done in an automatized way just here. So we come back to the subadditive closure. The subadditive closure of a function is simply to take the minimum between the function convolves once with itself, twice with itself, 3 times with itself, and so on, and the neutral elements, so essentially forcing it to pass to the origin here. And I take the minimum for that. So f of 0 is equal to 0 because of this element here. And it's easy to show that this function, if f is not subadditive, the closure is subadditive and passing to the origin. So essentially, it comes to the function. And in addition, it enjoys a number of nice properties if I take the subadditive closure of the minimum or of the convolution of functions when they pass through the origin. So if I apply that to the same thing, that's the function convolve with itself one time and so on. You see that each time I have something which is larger, so the minimum of all these functions, the subadditive closure of that, will be that function in red and the origin that I would need to put here. On the other hand, if I convolve this function in red with itself, I'll get the blue function, and then I'll get the green function here. So the minimum will go and will be something different from all the function here. It will be this green curve that I have just here. You see that even though the shape of the function looks the same, the subadditive closure can be quite different between the two of them. Okay, and here's the point, essentially, that marks the fact that I need to pass to the origin. So the subadditive closure, essentially, is what can replace any arrival curve. So if I have an arrival curve alpha, I can always replace it by the subadditive closure. So I can always do the minimum between delta 0, alpha convolve once with itself, 2 times with itself, and so on. And if I do that, and I take the minimum, that will be also an arrival curve. And that's the smallest of all possible arrival curves I can find. So essentially, that's the best I can have. If you gave me one, it has to conform to this flow here. Now, that's if you gave me an arrival curve. What happens if the only information that you have is measurements? For example, you give me this MPEG file, or this flow here, and I would like to compute an arrival curve based on measurements. Then I have to introduce the last operator I need for arrival curve, which is the deconvolution. It's the inverse of the convolution. So basically, instead of taking, so the convolution, remember, f convolve with j at time t is the infimum for all s between 0 and t of one of the function plus the other one like this. And that's the min plus convolution. The deconvolution, I put this thing, f deconvolve by j. Well, instead of taking the inf, I take the sup, so I take the largest value, and I shift the first function positively, and then I subtract instead of adding the other function, and I need to do that for all s larger or equal to 0. So that's the deconvolution, and it gives a function like this, okay, because of the sup if you do the operation. Now, you see that f and j, they are wide sense increasing function that starts at 0, that are 0 elsewhere here. F deconvolved by j, it's again a wide sense increasing function. Unfortunately, it's not in the set f because it's non-zero for a negative value of f. So it's not a closed operation in general. But if you deconvolve f by itself, so if this function is f again, then it's always in f. It's always subadditive and passing to the origin. And it has a duality with the convolution. That's why it's the inverse operation. So essentially, if you have f deconvolved by j, which is less or equal than h, well, I can replace that by saying f needs to be less or equal than h convolved by j or j convolved by h, which is the same here. Okay, so the two are the opposite for each other. And then how to compute the minimal arrival curve for measurements is precisely to deconvolve R by itself. Why? It's an arrival curve because if I take R of t minus R of s, well, I can rewrite R of t as R of t minus s plus s minus R of s. And so this is always less than if I run the sup here for all u that are larger or equal to 0. Because in particular, one particular u is to take u is equal to s, but I can take any value of u which gives me a larger difference between these two terms than this one, and I will have something larger or equal. And this is precisely the deconvolution of R by R. It's the sum of R of t plus u, of t minus s plus u, plus minus r of s, so if I evolve that in t minus s. So this is an arrival curve. And if I have another arrival curve that you gave me, then r must conform to this arrival curve, so r must be less or equal than r convolved with alpha prime. If I take this property, r is less than r convolved with alpha prime, well, it means that r deconvolved with r must be less or equal than alpha prime. But this was the arrival curve alpha, so alpha is less than alpha prime. So the minimal arrival curve is obtained from measurements simply as r deconvolved by r. So this is the flow r. This is the arrival curve that I obtained from these measurements. This is the arrival curve that I obtained from these measurement r just here. Okay, so that's for the arrival curve. So I would say for the arrival curve, okay, I have r conforms to an arrival curve alpha. Okay, means r of t minus r of s is less or equal than alpha of t minus s for all s between s and t. Equivalently, r of t is less or equal than r convolved with alpha at time t, if I use min plus convolution. And so that will characterize the traffic. Okay, if I have something, I will often look for an arrival curve to upper bound the amount of traffic that I can see in an interval S and T. Now, to derive backlog bounds and delay bounds, I need to characterize also all these elements. And I need to characterize them by what's called service curve. So essentially, a service curve defines a node model fairly abstract in an abstract way. So essentially, we don't want to look at necessarily how the scheduling is done, but we just want, because sometimes a complex interconnection of delay and scheduling elements, we just want to characterize the service that it offers. And in particular, even if the node is not work conserving, I can apply that to this setting. So how I define a service curve, and here I have a minimal service curve. So now I characterize this system, right, the system S. I have a flow X that enters. That's the cumulative flow X that enters. And I say that my system S offers a service curve here, which is beta of t, if there exists sometimes S, which is such that for any time t, the amount of traffic that has existed, the load that had exited the system at time t, is equal to all the traffic that has arrived until time s, plus the service curve over the remaining interval t minus s. So if I find an s so that x of s plus beta of t minus s has exited the system, and I find such an s for any time t, then I say that my systems here offer a service curve equal to beta of t. Okay? So for the service curve, so F offers beta as a service curve if for any time t there exists sometimes s less than t, such that the amount of traffic outside the system is at least all the traffic that has arrived until time s plus beta of t minus s. Okay, and if I do that, so if for any time t I can always find an s like this, well, I say that my service so essentially offers a guarantee on the amount of traffic that it exits. It's all the traffic that has arrived until sometimes s, and if I have something else over the remaining interval, I offer at least beta of t minus s. The most usual service curve that we use is this service curve here. So essentially, what does it mean? It means that, okay, until time s, everything has exited. Then I might have a server here, queue that goes on vacation, nothing happens. But then after this time, I exit data at the rate here equal to the rate of my rate latency curve, and I have that amount of data that must have exited the system. And so it's a guarantee that I have over how much traffic has exited the system by time t. That's a minimal service curve. So there is another service curve which is called a strict service curve, which is more intuitive, which is to say that if I have a backlog period, then the amount of traffic that exits the system between times s and t, so essentially y of t minus 1 of s, is at least equal to beta of t minus s. So if I have like a constant rate server, then I will have, so if this would be a constant rate here, then this would simply say that as soon as I start a busy period, okay, between st, then y of t minus 1 of s is larger or equal than c times t minus s. That's the amount of traffic that has exited the system. Now, it's a more demanding constraint, a strict service curve. It always implies that it has this service curve also as a minimal service curve. It's easy to see. You just take s as the beginning of the busy period. So if the buffer content is here, I'm at time t here. The beginning of the busy period is going to start from time s. Sorry. And I have a constant rate server here. Well, y of t minus 1 of s is simply equal to c t minus s because my buffer is always full between the two. And it's the beginning of the busy period, so all the traffic that has arrived up to time s exited at time s. It means that I find an s such that y of t is equal to x of s plus c of t minus s. So it means that the minimal service curve beta is equal to c times t, and c times t is a minimal service curve as well if it is a strict service curve. I can have other service curves which are not strict service curve. For example, the guaranteed delay node is another element in which I offer this as a service curve. What it means is that if this is the input flow, x, well, at any time t, I find a time s such that all the traffic that has arrived until time s has exited, and at least beta of t minus s. So if I am below t, then I know that I don't have any commitment. As soon as I'm above t, it's infinite. So essentially, it just guarantees that the maximum delay between the input and the output is no more than capital T here, the latency, which is just here. So that's another way to impose that I have a delay. And so this function here, which is a convex function, is another service curve. It cannot be a strict service curve because I cannot, during any backlog period that would last longer than this, offer an infinite amount of data outside. But it is a minimal service curve because for any time t here, I can always find a time s, which is less than capital T seconds before, such that all the traffic that has arrived on the red curve until time s has exited the system by time s plus something, which is such that the s plus something is less than little t. And again, we can express service curve with min plus convolution. Why? Because this guarantee here, the fact that y of t is larger or equal than beta of t minus s plus x of s for some s, well, if I have this for some s between 0 and t, I can take this s to be the one that achieves the infimum between 0 and t of that right-hand side. And if I take that, well, this is precisely the min plus convolution between x and beta. So in other words, for a service curve, I can again rewrite this by saying y, the output, must be larger than x, the input, convolved with beta. So the nice things with min plus convolution is that it characterizes both the service curve with an equality that the output is larger than the input convolved with beta, and the traffic envelope, the arrival curve, by saying R is less. I don't need to put, it's true for every t, so it's, I can drop this. R is less than R convolved with beta in this direction, means I don't go over the two. This envelope alpha, the two are like this. So this is the service curve that is the most used, because essentially it tells me I don't need to do anything during capital T seconds, but then I commit to exit data at a rate equal to capital R. Okay, so that's the most classical one to do. For example, I can have a situation like this ones and try to derive if I have two. So I have two flows here served by a queue at rate C. I have high priority traffic and low priority traffic between the two. And I try to find, so C is offered to the aggregate of the two, but I serve traffic here with priority over the low priority traffic. The maximum size of a packet in the low priority traffic is Lmax. So what is the service curve which is offered to the high priority traffic? Well, I just look at the equations. So what I find is that high priority traffic has always precedence, right? So the amount of traffic that exists between S and T is always larger or equal to C of T minus S, minus perhaps one packet that was in the server that needs to complete service, and that would be of length Lmax just here. And if I take S to be the start of the busy period for the high priority traffic, why the amount of traffic, high priority traffic that exited by time S is the same as the amount of traffic that entered at time S. So if I combine the two, well, yi of S is xh of S, and so that gives me one first equation. Now this equation here is again larger or equal to 0, so I take the maximum between this quantity here and this quantity here because S is less than T, and so that gives me a service curve for the high priority traffic. And the high priority traffic, actually it's a strict service curve, and therefore minimal traffic service curve is a rate latency with the rate C, and the latency being the maximum size of a packet actually multiplied by C to have the two there. If I do the same thing for the low priority traffic, then I need to constrain the high priority traffic by an arrival curve. And essentially, I need to redo the whole computation, but this time I need to subtract the arrival curve for the high priority traffic. Makes sense? Essentially, what I have is that for the low priority traffic, it's all the traffic that can exit the system minus the maximum amount of traffic that can arrive in the high priority between S prime and T. And so the service curve that I have for the low priority traffic is going to be this thing here. If I have a leaky bucket, so an affine service curve like this, then I get again a rate latency service curve, but this time the rate is the rate of the server minus the sustainable rate of the arrival traffic minus the burst size that I offer as for the high priority traffic. And this time it's only a minimal service curve. It's not a strict service curve. That's for the service curve. So once we have this, now we can find interesting properties. So remember, I am interested in the vertical difference between the two for the backlog and for the horizontal line for the delay. So the backlog is the vertical distance here, and the horizontal distance, which I can write this way, is going to be the delay of a bit entering here if things are served in the order at which they arrived. Well, if instead of having the input I have an arrival curve, and instead of having the output I have a service curve, I can find upper bound for the backlog, which is the maximum value of the vertical difference between the arrival curve alpha of the flow and the service curve of the element. And so this is the maximum value. I can express that using my convolution operator. You see that it's the convolution operator if I take t is equal to 0. So it's a deconvolution between the two curves at time t is equal to 0. And same thing here for the delay that I have just here. That's the vertical, horizontal, and the output flows. How to find that? Well, it's a tight band for backlog because the flow, so it's constrained by the arrival curve alpha. The system offers this service curve beta. The backlog is the vertical distance between the two, and so I have the difference between the two here. That's for the delay. And for the arrival curve of the output flow, this can be again computed as a function of the arrival curve of the input flow and the service curve of the system. Actually, so if I have a system that offers a service curve beta to the input flow, the output flow is constrained by an arrival curve which is alpha deconvolved by the service curve beta. To see that, well, sorry. So for the difference between the two things, actually it's sorry, y of t. Okay, this is less. And so y of t, x of t is larger or equal than y of t. There's a typo here. It should be a larger or equal. All the traffic that has arrived up to time t is larger or equal to all the traffic that has exited at that time t. That's just because I have a causal system. And all the traffic that has exited at time s, since the system offers a service curve beta, is always larger or equal than the min plus convolution between x and the service curve, which I write this way. So if I take y of t minus y of s, y of t is larger than x of t, minus y of s is going to be less than this quantity here. And so if I play with this, x of t minus the infimum, well, it's the sup of x of t minus x of u, because I have a minus sign, minus the infimum is plus the supremum. And this, again, since x of t minus x of u is less than alpha over t minus u, this is less than the maximum distance between alpha of t minus u minus beta of s minus u. If I put that equal to v, I have the supremum of alpha t minus s plus v minus b of v. Therefore, the deconvolution, if I look this, of alpha of t minus s plus v minus beta of v, so the deconvolution of alpha and beta. So if I have an arrival curve here, a service curve here, I automatically get an arrival curve for the flow at the output of the system. And I can continue like that all the way. If I have two systems offering service curves beta 1 and beta 2 that are concatenated with each other, so that are in tandem. So I have the first system here and the second system here, and I concatenate them one after the others. The service curve of the whole element is the min plus convolution of the two service curves here. So essentially, that's where these service curves are also powerful in the sense that I can have a long chain of different elements offering each a service curve beta 1, beta 2, and so on. Well, the service curve offered end-to-end is beta 1 convolved with beta 2, and I can replace this by an equivalent system as this one. So for example, if I have two routers, both of them offering, the first one offering a service curve which is a rate latency with latency T1 and rate R1, the second one with latency T2 and rate R2, well, the end-to-end service curve will be the min plus convolution of these two. Now, these two functions, they are convex function, so I take one of the rules of min plus convolution applying to piecewise linear function that are convex is simply that I take the different elements in order of increasing slope. So I have this one, slope 0. Next one is this one, slope 0. So I will have slope 0 until T1 plus T2. And then I take the minimum of these two rates. It seems that the R1 is smaller, so it will be, again, a rate latency curve, but I add the latency T1 to the latency T2, and I have the minimum rate R1, and that will be the service curve of the two systems. Okay, that I have just here. And so it's easy to compute in this way. Now, this has been useful to show things such as, for example, pay burst only once. So imagine that I have a flow here constrained by an arrival curve alpha that goes through a first router with a rate latency function B1 that goes over a delay D1. The worst case delay for the second one is D2. And I wonder if, so my arrival curve here, alpha, so alpha, sorry, here. So alpha, the rate latency curve, is going to be the affine curve, right? So it's going to be RT plus B, and then minimum delta of 0 of T as the rate latency curve. So this curve here. I have a burst B and a rate equal to R. And so if I look at the delay to the first router, right, I will compute the horizontal distance between the service curve and the arrival curve for the first router. Then I could compute the arrival curve of the flow here at the exit, and again take the horizontal distance between this arrival curve and the service curve of the second router that will give me the worst case delay D2 and add the two delay together. But actually that neglects the fact that the burst will not arrive exactly at the same time in both systems. If I convolve the two, okay, if I do this computation and I take the horizontal distance between the two, that's the expression that I obtain. If I take now the convolution of these two and I look at the end-to-end delay through this element here, and I do the same computation, I get this. So I get T1 plus T2, but the burst here is counted twice. It's counted once because I go to this element, it's counted a second time because I go to this element here. Here, since I have a single rate latency function, okay, as I had in the previous slides, so here I will have one function like this, so I will have one delay, which is this horizontal distance here. Here I will have the rate latency function like this, so I would have this delay here, and I add the two. Now, if I take the input rate latency function here, I will just have a distance, which is the sum T1 plus T2, but the burst is going to be counted only once. That's why we call this result pay burst only once. And the end-to-end delay is less, the bound on the end-to-end delay is less than if I compute the delay bound for each element separately and I add them up one after the others. So the advantage of composing first, finding first the service curve end-to-end and then computing the delay bounds is that you get much tighter bounds than if you compute the delay bounds on each element separately, one after the other. And so that's an advantage of this composition rule that we have just here. An element that is important, of course, for us is the greedy shaper. And so for the greedy shaper, essentially that's an element in which I exit data as soon as possible, but the output here must conform to an arrival curve sigma, which is the shaping curve. So essentially the output must be constrained by this arrival curve. So it means that for any ST, the quantity of traffic here that I see on the output link is going to be less than sigma of T minus S, and I store data in a buffer if I need it. And so what the shaper does, it maximizes, it finds the output X of T, that is the largest flow, such that first, it's less or equal than the input flow. That's because the system is causal, so the traffic that can exit cannot be more than the traffic that has entered into the system. And second, X of T has sigma as an arrival curve. If X of T has a sigma as an arrival curve, then X is less or equal than X convolved by sigma, and that's expressed by this expression here. So what I have here is to solve a system in which I have a function which is less than an exogenous function R of T, but also the function X of T is less or equal than an operator applies to X of T. So So if you look at that, it's a little bit like system theory. It's the equivalent, if I go back to classical system theory, to a differential equations with an initial condition. That's the kind of problem you certainly have solved in analysis, in system theory, and so on. You have an initial condition, and then you have a dynamical system described by ordinary differential equation in which the state evolves as a function which might be linear or nonlinear, so an operator applied to the state at time t. Well, in min plus algebra, and so this has one solution if pi here is a Lipschitz function, a continuous Lipschitz function, then you have one solution. If you have min plus system theory, it's a little bit different. So essentially what replaces the initial condition is the initial value of the function x of t cannot be larger than a of t. So first you have inequalities instead of equalities. You have one that depends on something given here, and then you have something which is recursive, which is given by this expression here. And the solution of this system is actually easier to find than the solution of an ordinary differential equation. The first question would be to know, does that always have one solution when there is here? Actually, since we have a set of equality, one maximum solution. So, because of course I could take something which is 0 and 0 here. 0 is going to be less than a of t, and 0 is going to be less than the operator applied to itself. So I have an infinite number of solutions, but does it have one maximum solution? What condition for the operators? Okay, and so the example we have is precisely a kind of a system like this, in which x of t is less than r of t, the flows that arrives in the shaper, and the second condition is that the output of my shaper must conform to an arrival curve sigma, so I have this equation here. So in this case, the operator is a linear operator in min plus theory because it's simply a linear convolution in min plus algebra that I have to do. And that comes from a residuation theorem in min plus algebra. Essentially, how to do that is by computing. You can compute explicitly the solution if you take this operator, apply it to the function a, but you don't apply it only once. You again do the subadditive closure of this operator. So you take the operator, you apply it 0 times, 1 time, 2 times, 3 times, 4 times, and so on, and you take the minimum of all that. And that will give you the maximum solution to this set of equations. So this thing here is clearly less than a because the subadditive closure of a is less or equal than a. And if you look at this, well, pi of a apply inside here would give me pi composed by pi, so it's also in the infimum, and that's why it also satisfies the second equation if you do it recursively all the time. And this has a solution whenever this operator is so-called upper semi-continuous. So that means that if I take the minimum or the infimum of pi applied to AI is the same as pi applied to the infimum of AI. It's true in practice for all the operators except the convolution that we have in our systems. So here, if I look at things here, what is going to be the result? Well, x of t less than r of t, x of t less than x applied to sigma. Well, I need to take the infimum of r convolved with sigma 1 times, r convolved with sigma 2 times, 3 times, and so on. And if I do that, I get this result here. Now this will be sigma convolved twice with itself, 3 times with itself. That's something we have seen before. It's the subadditive closure of the curve sigma here. If sigma is subadditive passing to the origin, the subadditive closure is the function sigma itself. And so if I take a shaping curve, which is an arrival curve, which I can always take as a subadditive closure, then essentially the output is equal to r times sigma. So the shaper offers as a service curve sigma, but I have an equality. I have something more than an inequality that I would have for the service curve, and that's the shaping curve that I have just here. So it plays the role of my convolution item here in the linear system. It's a shaper, essentially. Instead of having sigma of t as the impulse response of an RC circuit here, I have sigma, which is the shaping curve in which I want to shape the output flow. So the output flow will conform to an arrival curve given by sigma here, and that will be the impulse response of my system. And so if it is subadditive, I just have this. So the service curve of the shaper is also sigma, because instead of having this with an inequality, so here I have things with an inequality instead of having that with an inequality. Voilà, it came back. Okay, so that's what I have just here. Now, things that we can check is, you might wonder if R itself is constrained by an arrival curve alpha, and if I put another arrival curve sigma here for the shaping, is X of t going also to remain constrained by the arrival curve of the original flow alpha? Again, that's something easy to do. X is equal to R convolved with sigma, and R conforms to an arrival curve alpha, so R is less than R convolved with alpha. The fact that a convolution is associative and commutative allows me to switch alpha and sigma, and R convolved with sigma is again equal to X. So X is less or equal than X convolved with alpha. Therefore, alpha is an arrival curve for X as well. So X has two arrival curves, alpha and sigma. And so actually, if I take the convolution of these two, I have another arrival curve. So shaping cannot not be undone by shaping. So if this was already shaped before, well, this is going to be shaped both by the previous shaper and by this shaper as well. That comes from this arrival curve. A last result to show with the shaper is to see if I place a shaper between two networks, how much additional delay I pay for that. So I have an input flow here that enters the first network. The network is characterized by a service curve beta 1. Then it proceeds to another network, and the second network is characterized by a service curve beta 2. And then, in order to avoid too big bursts and so on, I decide to place here a shaper, so to again reshape a little bit the traffic at the output of the first network to make sure that it conforms to an arrival curve sigma, which is equal or larger or equal than the initial arrival curve of my flow. Now, if I do that, on average, I will delay some packets, right? Because suddenly I might have a lot of packets that exit from this network. Then I need to store them in this buffer and to exit them not too fast so that I conform to the shaping curve here. So the average delay is increased by such a system. Shaping is not for free. The question is the worst case delay affected by that or not? That's a fairly complex system to work with, right? But that's where calculus helps. Actually, R of t, so it's constrained, so the way to do that, well, the end-to-end service curve for the first system is the convolution of the two service curves, beta 1, beta 2. For the second system here is beta 1, beta 2, but I added a new element that has service curve sigma, because the service curve of the shaper is sigma, so I take the convolution of these three here. Now, if I look the backlog, which is it's the vertical distance between, for the first system, the arrival curve, and the service curve of the system. So the vertical distance between these two things here, which I can express by deconvolution by saying is the deconvolution of alpha, the first curve, by the second curve, beta convolved with beta 1 at 0. If I take the second system, I take the vertical curve between alpha, and this time beta convolved by sigma convolved by beta 2, so this curve here. And if I express that with deconvolution, I can put the deconvolution between alpha and the convolution of these three curves at sigma. But now I can play, again, with commutativity. I do that with sigma. And then deconvolution, convolution, one of the rules tells me that I can take the deconvolution of these two, deconvolve by these two here. So I have alpha deconvolved by sigma. But sigma is the same as alpha or is larger or equal, so alpha deconvolved by sigma, if I do that, is always less than alpha itself. If sigma was equal to alpha, so if I have the same shaping curve, alpha deconvolved by sigma would be exactly equal to alpha. So I get that the vertical distance here is the same as the vertical distance between alpha and beta 1 convolved with beta 2. In other words, this distance here for the second system is the same as the vertical distance for the first systems. So it means that the total backlog I have here is the same as the total backlog I have here, worst case backlog. So reshaping does not increase the worst case delay. So it's a bit paradoxical. I buffer packets, it increased the average delay, but the worst case delay is not affected by that. Reshaping, so you can reshape your traffic between different, sorry, that's for the backlog, and the delay is exactly the same, but the horizontal curve is used in terms of the vertical curve. So for the horizontal curve, essentially the distance between alpha and the convolution of these three is the same as the distance between alpha and the convolution only of beta 1 and beta 2 because of properties of deconvolution and convolution that I played just here. So in 2 lines, you prove something that would take probably many pages to do if you had to do it by hand, take S, T, and stuff like that. It goes very quickly to do that. And so, and it's very counterintuitive, right? Because if you simulate this, well, I mean, you add the queuing system in the network, it does affect the delay, but only the average delay or the delay distribution. I mean, you have more packets that are delayed, but the worst case delay remains absolutely the same, and you keep the same guarantee, so you can do reshaping for free in this context. And finally, packetizer. So I'm not going to spend too much time on that because it gets fairly technical. So the shaper presented before, that's for fluid systems, or you can adapt it if you have constant size systems. In practice, you have packets of different size, and so there is an element which we call the packetizer that transforms essentially a fluid flow into a left continuous curve like this if you give me all the size of this system. So it adds some distortion, but it's again something you can play with easily by putting after the shaper a packetizer of that kind. So the constant rate server will be a greedy shaper fluid type plus a packetizer that take the fluid and put it back in packets of the size that are given just before. Okay, now, I don't know if you are courageous to do the N example. Okay, so just to show you an example of how we can work with this kind of systems. So here it was a study that we did where you have a network characterized by a rate latency service curve, and you have a video server here on which you have different videos that you need to send on the network, but you need to smooth them. Okay, so you cannot send them at any rate. Then at the receiver side, you have a buffer B, you store them, and you play back the video after a playback delay D. So essentially, you have the video, little d here might be equal to 0, in which case you cannot prefetch data, or you could prefetch a little bit look-ahead data up to little d on the server, smooth them so that you don't send at full rate, you limit your rate here. It traverses a network, so it adds some jitter and delay as characterized by a rate latency service curve. You store it in the buffer, and you wait capital D unit of time before playing back that on the receiver. The question that I would like to ask is to say, okay, if I do that, you know, what is the minimal playback delay that I have? Do I need to wait long or not? And what also needs to be the size of the playback buffer that I need to have. So here I have different constraints. Of course, I don't want my buffer to overflow, but I don't want the buffer to be empty. Because if it is empty, you know, then it means I'm waiting for some frames of the video to arrive. I cannot feed that on the video display, and essentially I have something which is frozen, so that's something that we will explain. So I want to be I want to have this buffer always containing something to feed here, and not to overflow, not to underflow, not to overflow. I have a constraint, essentially sigma, so that's I cannot send data at an infinite rate here. I have some rate, sigma of t might be some r times t, so maximum rate at which I can send data. And I would like to have a playback delay which is as small as possible under this constraint. So how do we do that? So what are the minimum value of the playback delay and playback buffer given some look ahead that I have, which might be 0, right? I might not be able to look ahead if I have, for example, I don't know, a football game that is given live. I cannot preempt, but if I have video server, I can maybe prefetch some frames here and send them before. I have sigma, which is like the smoothing rate at which I can send things, and beta, which characterizes the network, which is what it is that I have just here. So how do I model the system? Well, I write all the inequalities that model the systems, and these are all the inequalities that I have. The first one, my unknown I'm going to play with is the flow at the input of the network just after the smoother or the shaper that I have just here. Okay, so x of t conforms to an arrival curve sigma because it's smoothed, it's shaped to conform by an arrival curve sigma. So that's this line here. X conform to arrival curve sigma that's expressed by this expression here. Now, x of t, it's a causal flow, so it has to be 0 for t less or equal to 0. It's just expressed by this equation here. And then x of t cannot be larger than a at time t plus d if I allow from some look ahead up to d time units. If I don't allow for d time units, I don't need this one, and then I have only this constraint here. I can cancel the d here. This is x of t. It cannot be larger than this. And then at the output flow, y of t, well, y of t must be such that it's always larger than a of t minus d. That's to prevent an underflow. Otherwise, I don't feed my display. So I need to have always data larger than a of t minus d. A is the same here. It's the movie that I play capital D time unit later. And I cannot overflow. So the amount of data that I have in the buffer, which is the difference between y of t and all what has exited a of t minus d, cannot be larger than capital B. And then I don't know y of t as a function of x of t, right? I want to keep something very general. I just know a guarantee offered by the network under the form of a minimal service curve. So y of t is some function of x of t. It's not known. All I know is that y of t is larger than x convolved with beta because my network offers a service curve beta here. So y of t, of course, cannot be larger than x of t. I need to have the data arriving first at the input before it can be shown at the output. So y of t is less than x of t. But I have a guarantee of service, so I know that x convolved with beta will have exited by time t. That's the guarantee I have. So how do I solve this? So this is the model, if you want. Well, again, I apply this theorem, right? So what I will have is, you see, there are some functions here that do not depend on x. This function depends on x. I have y of t that depends on two functions that don't depend on a, but y of t also depends on x. So I begin to have a fairly complex systems to model. I remind you this theorem that we have used. Well, I first transform the equations to remove the y, essentially. And what I do is y of t is such that y of t is larger or equal than x convolved with beta So if I impose that x convolved with beta is larger than a of t minus d, I'm fine, because I know that the output flow is always larger or equal than what is offered as guaranteed as a service curve. And so if this is larger than a of t minus d, I'm sure I don't have any buffer underflow. And vice versa, y of t is always less or equal than x of t, which is always less than a of t minus d plus b. If this is true, I don't have any buffer overflow. Okay, that's because if I come back 2 slides before, if y of t less than x of t, so if x of t is less than this, then I'm sure that y of t is going to be less than this. And if x convolved with beta is more than the right-hand side, then y of t is for sure also larger than 1 of t plus beta. So this way, I have rewritten the constraint in y in terms of x. Now, if x convolved with beta larger than a, if I want to isolate x, I remember then x convolved with beta larger than a is equivalent to here having a minus beta less or equal than x. So this is equivalent to this constraint here with the deconvolution. It's again the fact that convolution and deconvolution are dual from each other. So now I have all the constraints that I can put. I have this constraint here, which I find here. And I have x of t, which must be equal to the first constraint delta 0 of t, a of t plus d, this thing here, and that must conform to the rival curve sigma, which is just here. So again, we have this first equation here, which is an equation in which we can apply the residuation theorem because I have this independent term and an operator of applied to x. So how do I solve this? Well, residuation theorem, I take the operator here applied to this big function here, and I take the subadditive closure of all this. So sigma convolved with all this. Well, sigma convolved with the neutral gives me sigma. Sigma convolved with a of t plus d gives me this quantity here. And sigma convolved with a of t minus d plus b gives me this quantity here. I take the subadditive closure, but sigma being subadditive itself, the subadditive closure of a minimum of subadditive function is this function just here. So that's the output of the system. And I need to check that the output, okay, the maximal solution of this satisfies this. And so if I do that, if the maximal solution of this, which is this thing here, satisfies the other equation, then I have the minimum between 3 terms here, sigma of t, sigma convolved with a at time t minus d, sigma convolved with a at time t plus d. So the first one tells me sigma of t must be more than a deconvolved with beta at t minus capital D, and so that will give me the value of capital D, the playback delay, as actually the horizontal distance between E deconvolved with B and sigma, which I can rearrange again using mean plus convolution as the horizontal distance between the film, the video stored on the server, and the convolution of the service curve of the network and the shaper. If I take the buffer, I'll take the vertical distance. It will be given by the second equation, this larger than this. D is fixed by this. Then I get B, which is given by this quantity here. And the look-ahead delay will come here as the distance between not A, but A deconvolved by A, so the minimal arrival curve on A, and beta convolved by sigma. And so these are all the minimum value that I have. And so there is a minimum playback delay. What it tells me is that if you give me a service curve, so the network provider commits to a minimal service curve, which is this. I pay to shape with this arrival curve, and I have a video which is stored, which is A. The horizontal distance between this and this is the minimum playback delay that I must have in order to guarantee that I will never have a frozen screen that essentially I will not have any underflow. I need to be able to have a look ahead, which is equal to this, which is this horizontal distance, and the buffer at the end must be larger than this in order to guarantee correct operation. So if I take, for example, a 2 leaky bucket and a service curve beta, what I do is I compute the convolution between these two. That will be the convolution between these two. The second one is I compute the horizontal distance between the video stored on the server and this curve. That will be the minimum playback delay that I must have. So if I have a playback delay smaller than this, I might have some problems. If I have this playback delay, which is at least this, and everyone conforms to the commitment on beta for the service on the network, I'm fine. I compute A deconvolved by A and the horizontal deviation to have the look-ahead delay. You see that it's a bit bigger than here. That's if I allow the playback delay. If I don't have if I allow look-ahead delay. If I don't have look-ahead, that's what I need to take as a playback delay. Then I have to do that. And finally, I have the vertical difference between the two for the minimal size of the playback buffer. So if I do that, for example, on this MPEG file, this is the MPEG file. This is A of t, right? The MPEG file stored on the server. And that's E deconvolved by A, the minimal arrival curve on the file. If the smoothing curve sigma of t is r times t, well, the horizontal distance between these two will give me the minimum playback delay that I need to have. And this will be the minimum sum of the playback plus look-ahead delay. So if I have a possibility of look-ahead, that's what I need to do. Essentially, what will be a bit difficult to work with is this big chunk of data. See, that's essentially comes into play. And that's typically, as a function of R, what should be the playback delay? You see that if R is very small, then suddenly the playback delay is going to be very large. And that's the look-ahead delay that I could take. So essentially, here I have a very small playback delay, but because I can look ahead things, essentially these big bursts of data, I can prefetch and send it earlier if I have a rate which is large enough to absorb this thing. And then if the rate becomes very small, I cannot even prefetch these data. So basically, I delay them, and I have to increase the playback delay to absorb this at the end. So for example, that was for the Jurassic Park trace. Okay, you have some actions that take much more. And so the look-ahead delays, depending on how many frames you look at, the size and so on might be much larger or not. That's the playback delay, and that's the look-ahead delay. And it also depends on the position. So for example, if you take this chunk of data, and so on, if you look at the maximum playback delay for each of the different pieces, you'd see it's much higher depending on the rate, the smoothing rate R, just because here, well, you have a lot of data that you cannot necessarily prefetch so much in advance. But if you have the entire trace, well, you can prefetch this data in advance, and so you can organize your schedule much better and afford to have a much lower look-ahead delay by prefetching this frame and sending ahead of time. And how to compute that is just like putting, if you want, what I did just here is solving a set of differential equations in the dynamical system, but in min plus algebra, just to have the solution of all this. So conclusion, so it's a set of tools and theories for the deterministic analysis of communication networks with provable guarantees. And I think that's the part where people like it, is to have these provable guarantees. It gives new tools for analysis part, which are different, of course, than stochastic queuing systems. You see that essentially, I just play with min plus algebra. It looks more complex than what it is maybe the first time you see it, but it's just very simple rules that we apply just here for computing all these delays here. And I've even gone 5 minutes more this time than time since we started here. So I'm going to stop here with the introduction of so a short introduction of network calculus and what you can do with it. And so the text is available online here if you want to know more about this. Thank you very much. Yes?
So you showed the Airbus 380, yeah, and I mean Swiss does not have them, but others have it. So, but what was the?
Okay, but I found then it because I Google. Yeah, it's true. It's Lufthansa that has
So
the.
it was real. It's not. It's not.
I saw. I just Google A380 plus Swiss and then found this picture.
The AI made it up on the fly.
Yeah, probably.
No, I mean, what are the problems that were looked at there? Do you know?
So there, essentially, what they have is that they have schedulers with two priorities, and they need to compute essentially delay bounds for all possible combination of low and high traffic through more than 1,000 switches of one network. Yeah. So they have that. So if you read the paper, essentially the number of tests they have, if they do all the tests by hand, is 2 to the power 1,000 something. So it's like a humongous number of checks to be made. It's a little bit what Laurent was saying yesterday, essentially. So I think they use it to reduce a little bit the number of tests that they have to make by having a little bit more crisp guarantees on the delays that they can have thanks to network localization.
Each element that sends traffic and each element that consumes in these two different types of schedulers, and then computed all the.
Well, that's how I understood it, because the paper does not describe it. I mean, I didn't read completely the paper, but that's how I understood it from the paper. So the second stage is always like, how can we speed up a little bit the number of tests to do, but doing an exhaustive verification is like beyond that. So essentially this is, as I understand, the pre-processing step to limit the number of tests that you need to do in the second stage. That's how I understood that they used it in the network. But they did the paper that I went over to prepare this does not describe exactly how they make the junction of the two. They describe network calculus and then they say, okay, we have so many, 2 to the 1,000 something is like humongous, so we need to reduce it. That's how I understood it. Yes?
I have a question regarding how the beta function.
Yeah.
Changes for systems where the service time also depends on other queues that
That's a very good. So that's a lot.
CSMACA, right? You have to wait that the others have finished traffic before.
So a lot of the research done over the last 10 years is precisely to take that into account. Because here, basically, what I did is I said there's a system, it guarantees that service curve to the flow of interest, and I'm just looking to my flow of interest. The only case where I just briefly touched to the existence of two flows is one with high priority, one with low priority. And then, the low priority, if I have a traffic envelope, so an arrival curve for the high priority traffic, I can compute what residual service curve I can guarantee for the low priority. But I would say most of the research is precisely to take into account interfering traffic. And that's not so easy to do. So concatenating elements one after the others, even if you have complex service curve, that's easy to do. Because you just do this convolution, there's these little rules, you play with them, but I mean, you can automatize that, that's fairly easy. Now, if you have back traffic that comes in the back, then essentially it's the sum of the traffic, but the sum in min plus algebra boils on to the multiplication, right? So it's a non-linear composition of the traffic that enters the element. So you cannot cope with that very easily. And so there are different ways of trying to isolate this other traffic, but there's not a general recipe, I would say. You need to look really at how things are scheduled with the background traffic to do that. And much of the progress that I think has been made over the last decade is precisely in situations like that, which are very important in practice. But it's much more difficult. I mean, here I gave proofs that hold in one slide, one PowerPoint slide. There, essentially, we don't have that. We don't have that anymore. So the way to do is typically to introduce other operators. So a number of things can be done with other operators, and then to lower bound, upper bound these other operators in a smart way. So but that's, I would say, most of the recent progress that came in, and that is needed in network calculus. But that's not easy to take. So it's really difficult. Okay, thank you very much then for the attention. Then we stop here.